Hello there and welcome to Science for Sleep, the little corner of the universe where curiosity comes with calm edges and science takes its time. Tonight we're setting out on a journey through something so big that even the word big sounds laughably small when we try to apply it. We're going to talk about the size of the universe, not in quick facts, not in short numbers, but in a way that lets us really wander through it, pause where we need to, and feel its scale in the same way you might take in the view from a quiet hill at night. So before we start, let me ask you, where are you listening from tonight? And what does your sky look like right now? Maybe it's already dark where you are, and if you stepped outside you'd see a handful of stars, maybe dozens, maybe more if you're somewhere rural. Or maybe it's daylight where you are, and the stars are still there, just hidden, waiting for the sky to dim again. Isn't it a little funny to think of billions of stars overhead even when you can't see a single one? As you settle in, I'd like you to slow your breathing just a little. Let your thoughts drift the way they do when you're not rushing anywhere, because this is not a rush story. This is the kind of story that takes the scenic route. If you find this kind of slow science comforting, if it helps you to drift or to learn or maybe both at once, I'd be so grateful if you left a like or subscribed, because it helps other people find this same quiet space. For now though, there's nothing to do but listen. Let's imagine together the size of the universe and see how far we can travel in the mind before sleep finds us. When you think of size, the first things that come to mind might be objects you can hold, a mug, a chair, a car, things you can see in front of you. But the word big quickly slips out of its usual comfort zone once you look up at the sky. If I told you the universe is 93 billion light years across in observable terms, would that really mean anything on its own? Probably not, because none of us has a direct sense of what even 1 light year feels like. A light year isn't a measure of time in this context. It's a measure of distance. It's the span that light, moving at the fastest speed known in nature, covers in a single year. Imagine a beam of light leaving a torch, streaking out into the dark. In 1 second, it travels nearly 300,000 kilometers. In 1 year, it moves almost 10 trillion kilometers. 1 light year is 10 trillion kilometers. Already the mind stalls a little, because there's nothing in daily life even remotely close to that scale. 10 trillion kilometers is a number, but it doesn't really land in the body as an experience. And yet, when we talk about the size of the universe, we need light years not as exotic trivia, but as ordinary vocabulary. To get a foothold, we can start small. Imagine Earth. If you drove around the planet at highway speed without ever stopping, it would take you a few weeks to circle it. If you flew around in a plane, you might do it in under 2 days with layovers. If you were light, you'd circle Earth 7.5 times in 1 second. Already, light makes a mockery of our familiar sense of travel. The Moon, our nearest neighbour in space, is about 1.25 light seconds away. That's how long it takes for a radio signal to travel between Earth and the Moon. When astronauts left Earth for the first time, it took them about 3 days to get there. Light does it in about 1 second. The Sun, by contrast, is much farther. It takes light about 8 minutes to travel from the Sun to Earth. So when you step outside at noon and feel warmth on your skin, you're actually feeling sunlight that left the Sun 8 minutes ago. If the Sun somehow vanished, we wouldn't know until those 8 minutes had passed. Think of that. Even the thing that seems closest to us in space, our star, is far enough away that information about it takes time to reach us. That delay is small compared to the scales we're going to explore, but it's the first reminder that the universe is simply too large to ever feel immediate. Everything we know about space comes to us after a journey. Now imagine travelling outward past the Sun. The farthest planet, Neptune, orbits at a distance of about 4 light hours. That means light from the Sun takes 4 hours to reach it. If Earth were the size of a coin in your pocket, Neptune would be hundreds of meters away, and even then you'd still only be at the edge of our planetary system. Beyond Neptune lies the Kuiper Belt, a region filled with icy bodies and dwarf planets like Pluto. Beyond that, we eventually reach the Oort cloud. a vast shell of icy debris thought to surround the solar system like a bubble. The outer edge of that cloud might be a light year away from the sun, maybe even more. It's so far out that we've never seen it directly. We only infer its presence from the comets that occasionally swing in toward us, long tails of ice and dust evaporating as they pass through sunlight. 1 light year just to get to the edge of our own backyard. And beyond that, the stars begin. Our nearest neighbour, Proxima Centauri, is about 4 light years away. If you left Earth on the fastest spacecraft humans have ever built, you wouldn't get there for tens of thousands of years. For light, 4 years is quick. For us, it's forever. And Proxima Centauri is only the nearest. The Milky Way, our galaxy, contains hundreds of billions of stars. It's shaped like a spiral disk, a great glowing wheel of starlight about 100,000 light-years across. Picture that for a moment. If you were at one edge of the Milky Way and fired a beam of light toward the opposite edge, it would take 100,000 years to arrive. Civilization as we know it hasn't even existed for a fraction of that time. And yet, that's just our galaxy, one among billions. But before we rush outward, it's worth pausing in this neighbourhood we've already sketched. Because even here, in the scale between Earth, Sun and nearest stars, the human mind begins to wobble. 1 second, 8 minutes, 4 years, 100,000 years. Each step adds another layer of immensity, and we're only just starting. As you listen, you might already be feeling that curious mix of awe and distance that comes when we talk about cosmic scale. On one hand, it's exhilarating to imagine. On the other, it's impossible to really picture. Our imaginations weren't built for trillions of kilometers or billions of stars. But we can build bridges using comparisons, using metaphors that anchor these numbers to something closer to us. If the sun were a single grain of sand, then the Earth would be a speck you'd barely see, orbiting a few centimeters away. Proxima Centauri would be another grain, 400 meters down the beach. And the Milky Way, that would stretch across continents. These kinds of metaphors are clumsy, but they help us glimpse just how much bigger the universe is than our instincts suggest. When ancient people looked at the night sky, they saw only points of light, all seemingly near one another, sprinkled on a black canvas. To them, the heavens looked like a dome, a ceiling, perhaps not so far away. It took centuries of careful measurement to realize the stars are not painted on a shell, but scattered at wildly different distances, some near, some unimaginably far, some gone already but their light still streaming toward us. Every twinkle in the sky is an ancient message. Some of those photons left their stars before humans had even evolved. To look at the night sky is to see deep into time as well as distance. When we start talking about the size of the universe, the word distance quickly stops behaving the way we expect. In everyday life, distance is simple enough. You can walk across a room in a few steps. You can drive to a nearby shop in a few minutes. Even long distances like road trips across countries still sit within the frame of days or weeks. You can imagine them, plan them, break them into chunks of hours. But once we try to stretch that sense of distance into space, it collapses almost instantly. The scales are too large, the numbers too strange, and the mind does what it always does when it's overwhelmed. It tries to shrink things back down to something familiar. Think about the way we measure distances here on Earth. A meter is about the length of your arm. A kilometre is the sort of thing you might walk in 10 or 15 minutes. 1,000 kilometres is something a plane might cover in a couple of hours. These measures are comfortable, tangible. But when astronomers began measuring the heavens, they quickly realised that no unit from daily life would work. Kilometres and miles were swallowed up by the sky almost immediately. So they started with something else, the distance from the Earth to the Sun. They called this the astronomical unit, or AU for short. 1 AU is about 150 million kilometres. That's the gap our planet orbits across every single year. To you and me, 150 million kilometres is ungraspable. But in astronomy, it's barely a first step. Using astronomical units works fine within our solar system. Mercury is less than 1 AU from the Sun. Mars is about 1.5. Jupiter, the giant of our planetary family, sits around 5 AU away. Neptune, the distant blue world with supersonic winds, is 30 AU from the Sun. That's already 4.5 billion kilometres, but astronomers shrug and note it casually, because in the bigger picture it's still local. Beyond Neptune, the scattered icy fragments of the Kuiper belt stretch farther still. Eventually we arrive at the Oort cloud, perhaps 50,000 AU away. At that point, even the AU starts to feel too small. The numbers get clunky. We need another unit. Enter the light year. A unit not based on Earth, not even based on the solar system, but on the speed of a light itself. A light year is the distance light travels in a year, nearly 10 trillion kilometres. This number is not friendly. If you tried to write it out, it would have 13 digits, and if you tried to compare it to something ordinary, you'd tie your thoughts in knots. So instead, let's try an image. Imagine a car driving along a highway at 100 kilometers per hour, steadily, without ever stopping. To travel 1 light year at that speed, the car would need more than 10 million years just to cover one. And remember, our nearest star beyond the Sun, Proxima Centauri, is 4 of those light years away. This is where the human imagination starts to wobble. Numbers that high don't slot easily into our sense of scale. You can picture a year, or even 1,000 years if you stretch your mind across history books and ancient ruins. But 10 million years? That's older than entire species, older than many mountains, and yet that's the driving time for just a single light year. It gets stranger when we think about what seeing means at these distances. When you look at Proxima Centauri in the sky, the light hitting your eyes left that star 4 years ago. You're never seeing things as they are. You're always seeing things as they were. For the Sun, the delay is 8 minutes. For the Moon, it's just over 1 second. But for the stars, it's years, centuries, sometimes millennia. Look at the Andromeda galaxy on a clear night, and the light arriving tonight left 2.5 million years ago, when early humans were just beginning to shape tools from stone. In that sense, stargazing is also time travelling. The farther you look, the older the picture becomes. The universe reveals itself only after long journeys of light, and those journeys are limited. Light doesn't just travel forever into our view, it has to start somewhere, and it takes time to reach us. The most distant galaxies we've detected are over 13 billion light-years away. That means their light began its trip when the universe itself was young, less than 1 billion years old. Looking at them is like peering through the most ancient photographs imaginable, the snapshots of a cosmos just learning to assemble stars and galaxies. To make these distances more tangible, astronomers often use scaling analogies. One classic one is to shrink the entire observable universe down to the size of Earth. If the universe were Earth-sized, our solar system would be smaller than a virus, invisible to the naked eye. The Milky Way, our galaxy, would be no more than a fingerprint pattern smeared across a square inch. And the billions of other galaxies? They'd be like faint scattered grains of dust spread over every field, every ocean, every continent. Even these metaphors strain. You swap one incomprehensible number for another, but they do point out something important. The universe isn't just big in the way a mountain is big. It's big in a way that erases the usual categories. It's not a bigger house or a longer road. It's a bigness that mocks comparison itself. Our minds try anyway. We build mental ladders. First, the Earth to the Moon, then the Sun, then the nearest stars, then the galaxy, then the clusters of galaxies. Each step takes us farther from the ground we know, and each step makes the next one harder to picture. The scale grows not linearly but exponentially. You add a 0, then another, until the numbers stop looking like distances and start looking like abstract codes. But here's the curious part. Even though we can't really picture these distances, we can measure them with extraordinary accuracy. Astronomers use parallax, the tiny shift in a star's position, as Earth orbits the Sun, to calculate how far away it is. For more distant stars, they rely on standard candles, special kinds of stars that burn with a known brightness. By comparing how bright they appear to us, they can estimate distance. For the most far-flung galaxies, they measure the redshift of light, the stretching of wavelengths as the universe expands. Layer upon layer of clever methods, each one extending our reach a little farther until we're sketching maps of billions of light years. This is the paradox of cosmic distance. We cannot picture it, but we can measure it. We cannot feel it, but we can calculate it. And those measurements are consistent, repeatable, and reliable. They tell us that the observable universe is about 93 billion light-years across. Just saying the number is almost meaningless. 93 billion? What is that compared to? Nothing in daily life even brushes against it. Yet it's the best answer we have. It's tempting to call this unimaginable. But perhaps the better word is unfamiliar. We can imagine it in pieces: a second of light, a minute, an hour, an AU, a light year, a galaxy. Each piece slots into the next like stepping stones across a river. You never hold the whole river in your mind at once, but you can make your way across one stone at a time. That's how science has always handled scale. Piece by piece, measurement by measurement, until the unimaginable becomes at least discussable. And that's what we're doing now. Not grasping the entire size of the universe in one gulp, because no one can. But tracing its distances step by step, marvelling at how each one grows beyond the last. The more you stretch your mind to hold these scales, the more you realise how small our familiar world is. Not in a dismissive way, but in a grounding way. Our room, our city, our planet, all of them are tiny cradles of familiarity inside a cosmos so large that it takes light itself billions of years to travel across it. So when you look up tonight, or any night, and see a star, remember that what you're seeing is not simply a point of light. It's a messenger that has crossed an unthinkable gulf to arrive in your eye. It's a traveller from the past, carrying news of a place you will never reach in person, but which still shares its story with you across time and space. And if you let yourself, just for a moment, imagine what it means that there are not just a few stars, but hundreds of billions in our galaxy alone, each with its own distance, each with its own story, you might begin to feel why distances in the universe are not just numbers. They're part of the fabric of everything we are. When we speak of our place in the universe, it helps to pause for a while in the neighbourhood that feels closest to us. Because before we stretch into galaxies and webs of galaxies, there is a space much nearer, filled with familiar companions that shape our days and nights in ways we often forget to notice. It begins with Earth, of course, our home, but quickly extends to the worlds, moons and smaller bodies that circle our sun together with us. This is the patch of space we know best, not because it is small by any normal standard, but because we have lived beneath it, studied it, and sent our probes and spacecraft to wander across it. It is both vast and intimate at the same time, a kind of cosmic front yard. Think of the moon first, our only natural satellite, and the object in the sky that has most deeply shaped the rhythms of human life. Its gravity tugs on Earth's oceans, giving rise to tides. Its light, reflected from the sun, has guided people for tens of thousands of years through dark nights. Cultures across history have traced its cycles, marking months and seasons by the phases of its face. It is close in cosmic terms, just 1¼ light seconds away. A radio signal from Earth takes that long to reach it. But when astronauts first made the journey, it took them 3 days. The moon is near enough to imagine standing on, yet far enough that every trip there was an extraordinary feat. And to this day, when you see it rise, you're watching a companion world that circles us steadily, locked to us in a dance as old as our planet itself. From the moon, it feels natural to glance toward the sun, the great anchor of our neighbourhood. Nearly all the light and warmth that makes Earth livable comes from its nuclear heart, where hydrogen fuses into helium, releasing energy that radiates outward in a steady blaze. It takes photons hundreds of thousands of years to wander their way out from the sun's core to its surface, but once they escape, they stream through space at light speed, arriving at Earth in just over 8 minutes. We depend on this consistency more than anything else in the sky. The sun's gravity holds the planets in their paths, its energy drives weather, photosynthesis, the balance of climate. It is both an ordinary star, one of billions, and the most extraordinary thing in our skies simply because without it, we would not exist. Orbiting alongside us are the planets, each one its own story. Mercury, the small battered rock closest to the Sun, races around in just 88 days. Its surface is scorched by sunlight, but its nights are freezing, extremes born of a thin atmosphere that cannot soften the swing. Venus, thick with carbon dioxide and cloaked in acid clouds, is nearly Earth's twin in size, but nothing like it in nature. Its greenhouse atmosphere traps heat so efficiently that its surface could melt lead. For a long time, some imagined Venus as a lush jungle world. Now we know it as a furnace, a reminder of what runaway climate can do. And then there is Mars, red and dry, but endlessly fascinating. Its valleys, canyons, and polar caps hint at a past when water flowed more freely. Robotic explorers crawl its surface today, sending back images that stir both science and imagination. Many dream of standing there one day, looking back at Earth as a small dot in the sky, much as Apollo astronauts once looked back from the Moon. Mars is not close, not in human travel terms. Depending on orbits, it takes months to reach, but in the scale of the universe, it is right next door. Beyond Mars lies the realm of giants. Jupiter, with its swirling storms, coloured bands, and moons that are worlds in their own right. Europa, icy on the outside but hiding a vast ocean beneath, makes scientists wonder about the possibility of life. Ganymede, larger than Mercury. Io, alive with volcanic fire. Saturn follows, majestic with its rings, bands of icy particles circling in intricate shimmering arcs. Its moon Titan has lakes of liquid methane and a thick orange sky. Another moon, Enceladus, sprays fountains of water ice into space from cracks near its south pole, another possible harbour for life. The neighbourhood grows stranger the farther we go. Uranus, tilted so far on its side that it seems to roll through its orbit. Neptune, deep blue, with winds faster than sound. And Triton, its largest moon, moving in the wrong direction around it, as though it were captured rather than born there. All of these worlds, each so different, each orbiting in the same shared system, bound by the sun. And still, the familiar neighbourhood doesn't stop there. The dwarf planets add their own stories. Pluto, once called the 9th planet, remains a world of mountains and plains of nitrogen ice. Eris, Haumea, Makemake. Names less well known, yet each a world orbiting in the cold stretches beyond Neptune. Together they remind us that the solar system isn't just the tidy lineup of 8 planets we learned in school. It is a far richer family, filled with hundreds of thousands of smaller bodies, from asteroids in the belt between Mars and Jupiter to comets with their long glowing tails. It's easy to forget that all of these bodies, from Mercury to Pluto, from Ceres in the asteroid belt to comets swooping in from deep space, are orbiting together around the Sun. It is like a cosmic city, every object moving in paths defined by gravity, every one of them tied to the same central star. To look at the solar system as a whole is to see a neighbourhood in motion. The planets do not hang still in the dark. They speed along in orbits, Mercury whipping around quickly, Neptune crawling slowly. Earth, our home, completes its lap in 1 year. Each body keeps its rhythm, and together they form a complex dance that has gone on for billions of years. When you zoom out far enough, The solar system itself becomes just one speck among many. But from within, it is rich with detail. We've sent spacecraft to most of the planets now, each mission expanding our view. We've orbited Jupiter and Saturn, landed on Venus and Mars, flown past Pluto, even touched an asteroid to bring back samples. These achievements remind us that while the distances inside our neighbourhood are still huge, they are within the reach of exploration. They are not beyond imagination, not beyond technology. They are the frontier that humankind has begun to cross. And yet, even with all of this familiarity, the solar system remains immense compared to our daily experience. Light takes 8 minutes to reach us from the Sun, 4 hours to reach Neptune, more than a year to leave the Oort cloud. The scale dwarfs anything on Earth, and yet we think of this as local, our front yard, our neighbourhood. That phrase alone tells you how big the universe beyond must be. If this vast system of planets, moons and icy debris is only the starting ground. Still, there is comfort in knowing the details of this region. We can point to Mars and know roughly how long it would take to get there. We can track the orbits of asteroids and predict their paths. We can model the behaviour of comets. These things are not abstract. They are measurable, predictable, tangible in a way that galaxies and cosmic webs are not. They are the stepping stones between us and the wider unknown. Sometimes, when you see an image of the solar system laid out on a page, it looks neat, tidy, with planets lined up in order like beads on a string. But the reality is so much more spacious. If Earth were the size of a marble, the Moon would be a few centimetres away, the Sun a few metres. Jupiter would be dozens of metres off, Neptune hundreds. And the Oort cloud, the shell of icy fragments that marks the true edge of the Sun's influence, would be kilometres away. Space between worlds is vast compared to the worlds themselves. Most of the solar system is empty, scattered with occasional travellers. That emptiness is part of its character. It is not a crowded neighbourhood, but a spread out one. Yet for all its emptiness, this neighbourhood is where every story of life we know has unfolded. The Earth with its oceans and forests, the Moon with its pale glow, the Sun with its endless energy. These are not just landmarks in a cosmic map. They are the anchors of our existence. Every breath you take, every step you walk, every night you look up, you're inside this neighbourhood, part of its motion. And no matter how far our thoughts reach, it is from here that we always begin. The farther you go from the warmth of the sun, the quieter and stranger the neighbourhood becomes. Near Earth, space is busy. Satellites orbit, the moon hangs close, and the sun fills the sky with light and energy. But step outward, past Mars, past Jupiter with its swirling storms, past Saturn with its bright rings, and you begin to notice a shift. The sunlight weakens, the planets grow fewer and farther apart. By the time you've reached Neptune, the last of the giant planets, you're already in a place where the sun is no more than a brilliant star, far brighter than the others, but no longer filling the sky with heat. And beyond Neptune, the familiar fades almost entirely. This is the region we often call the outer reaches of the solar system. It begins with the Kuiper Belt, a vast ring of icy bodies stretching beyond Neptune's orbit. Here, dwarf planets like Pluto, Haumea, and Makemake drift in the cold, along with countless smaller objects that never quite became planets. The Kuiper Belt is sometimes compared to the asteroid belt, but it is far larger, extending billions of kilometres across and containing far more material. To visit it is to enter a zone where worlds are small, surfaces are frozen, and sunlight is weak. Pluto, once thought of as the 9th planet, is now understood as one of the brightest and largest members of this icy collection. Its mountains, plains, and nitrogen glaciers reveal that even in such cold, faraway places, geology still works. Other objects in the Kuiper Belt are less explored but no less fascinating. Some are elongated, spinning rapidly. Others are pairs, locked together in binary orbits. Many are too small and distant to study well, but they remind us that the solar system does not end with the neat row of planets we learn in school. It spills outward into icy frontiers, but the Kuiper belt is not the end. Beyond it, space becomes even emptier. Yet astronomers believe that surrounding the Sun, stretching out perhaps halfway to the nearest stars, lies a vast spherical shell of icy debris called the Oort cloud. Unlike the Kuiper belt, which lies in a relatively flat plane, the Oort cloud is thought to surround the solar system in all directions, a bubble of comets waiting in the dark. Its existence has never been directly observed. Instead, it is inferred from the orbits of long-period comets, those icy visitors that sweep inward only once in thousands or millions of years. To send a comet on such a path requires a reservoir far larger than the Kuiper belt. The Oort cloud, if it exists as theory suggests, would contain trillions of icy bodies, each one a frozen remnant of the solar system's birth. Imagine for a moment what it would be like to drift outward toward this shell. For days, months, years, you would travel beyond Neptune. The planets would vanish behind you, growing smaller until they were just dots of light. The sun itself would shrink in the sky, still brighter than anything else but no longer a blazing disk. By the time you reached the Kuiper belt, you would find yourself in a region more like an icy desert than a crowded field. Distances between objects would be enormous. Pluto, for example, is separated from its neighbours by millions of kilometres. You would not see bodies clustered like pebbles on a beach, but scattered like lonely boulders in an endless plain. And beyond that, the distances grow so great that the objects of the Oort cloud would likely never appear within sight. Even if you passed close to one, it might only look like a faint speck against the stars. The outer reaches test our imagination because they are so rarely encountered. No spacecraft has ever reached the Oort cloud. A handful, like Voyager 1, Voyager 2, Pioneer 10 and Pioneer 11, are travelling outward and may one day enter that region. But they move slowly compared to the scale. Voyager 1, the most distant of them all, launched in 1977, has travelled more than 20 billion kilometres from Earth. That sounds astonishing, and it is. Yet by most estimates, it has not even reached the Oort cloud. At its current speed, it would take thousands of years. That gives a sense of just how immense this outer shell must be. This part of the solar system is also where the sun's influence begins to wane. Within the planets, the solar wind, a stream of charged particles flowing outward from the sun, fills space. But at great distances, the pressure of interstellar gas pushes back. There is a boundary, called the heliopause, where the sun's wind stops dominating and the space between stars begins. Voyager 1 has likely crossed this boundary, making it the first human-made object to enter interstellar space. Yet even there, the sun's gravity still holds sway. The Oort cloud, if real, remains bound to the sun. It is part of our system, even if it lies light years across. The outer reaches also carry a kind of mystery. Some astronomers suspect there may be a hidden planet far beyond Neptune, sometimes called Planet 9. Its presence has been suggested by the odd clustering of certain distant orbits. If it exists, it could be several times the mass of Earth, orbiting hundreds of times farther from the Sun than we do. Finding it is difficult, because at such distances it would be faint and slow-moving, lost among countless stars. Whether or not it is real remains uncertain, but the very fact that astronomers consider the possibility shows how little we know about our own cosmic backyard. It's worth remembering that all of these outer regions are remnants of the solar system's formation. 4.5 billion years ago, the sun and planets formed from a swirling disk of gas and dust. Not everything was swept into planets. Some material was flung outward, far beyond the main system. Those icy fragments became the Kuiper belt and Oort cloud. They are leftovers, frozen archives of the solar system's earliest days. When we study comets, we are touching that ancient history directly. Their ices contain clues about the conditions when the sun was young. In daily life, the outer reaches feel irrelevant. They're too far, too cold, too empty. Yet they matter because they mark the true size of our solar system. The Sun's family does not end at Neptune. It stretches trillions of kilometres outward, blending eventually into the stars. When you look at a comet streaking through the night sky, with its glowing tail and fuzzy head, you're witnessing a traveller from those distant reaches, a messenger from the edges of the solar system. Its journey inward is a reminder that the outermost regions, though unseen, are real, and they occasionally reach out to touch us. If you could step outside the solar system entirely and look back, what you would see would not be a tight cluster of planets. You would see a small star orbited by tiny points too faint to notice. Only with powerful eyes could you make out the wide disk of debris, the faint halo of the Oort cloud. From that vantage point, even the outer reaches would look small, and yet from within, they stretch farther than we can travel, farther than we can currently imagine reaching. There's a strange beauty in knowing that the solar system, our home, is not a neat line of planets, but a sprawling, uneven system of worlds, belts, and clouds. The outer reaches remind us that edges are rarely sharp in space. They are fuzzy, fading, blending into the next scale. Just as the solar system blends into the galaxy, the Kuiper belt and Oort cloud blend into interstellar space. It is less like stepping across a line, and more like walking into a mist that gradually becomes another landscape. Beyond the Oort cloud, the sense of home begins to dissolve. Up until now, we've still been speaking of the solar system, even if in its widest, most distant form. The Kuiper belt, the scattered icy bodies, the trillions of frozen remnants that might make up the Oort cloud, all of these are still under the pull of the sun. They are family, however distant, however forgotten. But past that, the grip of our star begins to loosen. The sun's light grows dimmer until it is no brighter than the countless other stars in the sky. The warmth is gone. The solar wind no longer dominates. And at some point, after a distance so great it is almost meaningless to number, you step beyond the boundary where our solar system ends and the galaxy itself begins. This region is not well mapped. It is not filled with dramatic features or glowing landmarks. Instead, it is mostly emptiness. Between stars, the distances are so large that even the word vast feels inadequate. The nearest star to our Sun, Proxima Centauri, lies more than 4 light-years away. That means if you left Earth and aimed yourself directly toward it, you would cross through 4 years of light's journey in darkness before you arrived. Light covers nearly 10 trillion kilometers every year. Multiply that by 4, and you get a gap so enormous it hardly seems real. This gulf is what lies beyond the Oort cloud, the realm between stars. Space here is not entirely empty. It contains thin gas, mostly hydrogen, drifting atoms left over from the birth of the galaxy. It contains dust, tiny grains that can scatter light and sometimes gather into denser clouds. It contains magnetic fields and cosmic rays, high-energy particles that have wandered for millions of years, but to human senses it would feel like nothing. The density of matter in interstellar space is so low that if you scooped up a cubic centimetre, it might hold only a single atom. Compare that to the air you're breathing now, which contains billions of molecules in the same space, and you begin to see just how empty it is. And yet, this near-nothingness is the backdrop for everything. Stars are born in the denser pockets of this interstellar medium. Nebulae, those glowing clouds we see in photographs, are the nurseries where gravity pulls atoms together until fusion ignites. In other regions, stars explode as supernovae, scattering heavy elements, carbon, oxygen, iron, into the gas around them. Over time, those elements become part of new stars, new planets, new life. So while the space between stars feels empty, it is also the great cycle from which galaxies renew themselves. If you picture leaving the Oort cloud and drifting into this space, the sun would slowly fade behind you. At first, it would still be the brightest object. But gradually, as you moved farther, it would shrink until it looked like any other star. You would not know which one was yours unless you carried a map, and surrounding you in all directions would be thousands of other points of light, each one a star, each one its own system with its own planets, moons, and perhaps life. The loneliness of interstellar space is softened by the knowledge that every dot is another sun, another potential home. The distance to the next star is not just a number, it is a limit. Our fastest spacecraft, the Voyagers, moving at over 60,000 kilometers per hour, would take tens of thousands of years to reach even the nearest star. Tens of thousands of years is longer than all of recorded human history. That means, in practical terms, the stars are unreachable to us with current technology. The gulf beyond the Oort cloud is not just physical, but existential. It reminds us of the scale of separation built into the galaxy. And yet, the stars speak across that distance. Their light reaches us. Radio waves, natural or artificial, travel the same way. In theory, if another civilization exists around a nearby star, their signals could cross this void just as ours can. The distances are immense, but they do not silence. They only delay. A message from Proxima Centauri would take 4 years to arrive. A message from a star 20 light-years away would take 20. Conversation across interstellar space would be slow, but not impossible. That possibility has long stirred imaginations because it reminds us that the gulf is not absolute. It is a barrier, but one light can cross. This realm beyond the Oort cloud also carries a shift in perspective. Within the solar system, the sun is always the centre. Every orbit, every motion, every measurement refers back to it. But once you are between stars, there is no clear centre. The galaxy stretches around you in all directions, a disk of hundreds of billions of stars. You're no longer in a system, you're in a sea. The sense of belonging to one star fades, and you begin to feel instead part of the larger collection. For the first time, the solar system is no longer the framework, the galaxy is. Astronomers often describe this interstellar space as harsh, filled with radiation, far colder than any place near a star. Yet it is also serene in its scale. Imagine floating in darkness surrounded by stars. There is no up, no down, only a scattering of points across infinity. The silence is complete, the emptiness almost perfect. But in that emptiness, the history of the galaxy is written. Every atom drifting there may have once been part of a star, a planet, a living being. Over billions of years, matter circulates, broken apart, reassembled, reformed. Beyond the Oort cloud, you're not leaving something behind. You're entering the wider cycle. Sometimes, when astronomers speak of the galaxy, they use the term local bubble. This refers to the region of interstellar space our solar system currently sits in, a cavity carved out by past supernovae. We live inside this bubble of lower density gas, a region shaped long ago by dying stars. Beyond the Oort cloud, you're not just in empty space. You're inside the history of explosions, births, and collisions that built the Milky Way. The sun itself was born in a cluster of stars, and those siblings long ago drifted away. Somewhere out there, they still shine. The gulf between stars may feel uncrossable, but in the scale of the galaxy, it is the basic unit. Just as the gap between planets defines the solar system, the gap between stars defines the galaxy. Each step outward adds another layer of distance, from the moon to the sun, from the sun to the Oort cloud, and now from the Oort cloud to the nearest stars. Each step lengthens the measure until it no longer fits in ordinary thought. But that is the rhythm of the universe, always larger, always farther, always stretching the imagination. When you stand on Earth and look up at the night sky, you are already seeing beyond the Oort cloud. You are seeing interstellar space filled with stars. Every constellation, every twinkle, every faint band of the Milky Way is part of this realm. It is not a place you visit by travelling outward. It is a place you see every clear night, without leaving home. The only difference is that you are inside the solar system looking out, To actually be out there, between stars, would be to live inside the view itself. When you finally step far enough beyond the fading influence of the sun, the other stars around us begin to take on more presence. From Earth, they are pinpricks in the night sky, tiny points of light that twinkle because of our atmosphere. Out here, where there is no air to blur or scatter their glow, they would shine as steady beacons. And though each looks small, each is a sun, enormous and burning, with its own gravity, its own system, and its own story. Meeting our stellar neighbours means seeing that we are not alone in this sea of light. The very closest of them is Proxima Centauri, a small red dwarf star just over 4 light-years away. It is so faint that you cannot see it with the naked eye from Earth, even on the darkest night. Yet it is closer to us than any other star except the Sun. Proxima is a reminder that most stars in the galaxy are not grand, bright giants, but small, dim ones. Red dwarfs like Proxima burn slowly, with lifetimes measured not in billions but in trillions of years. If the universe lasts long enough, they will be the final stars still shining, long after larger suns have burned out. And even this tiny neighbour has planets. Astronomers have detected at least 2, one of them orbiting in the zone where liquid water could exist. Whether that world is barren or alive, we do not yet know. But its very presence suggests that planets are not rare, even around the smallest of suns. Nearby, within the same star system, are Alpha Centauri A and B, 2 stars locked in orbit around each other. Unlike Proxima, these are bright, sun-like stars, visible from Earth's southern hemisphere as a pair of points. They are closer to each other than Earth is to Saturn, circling one another in a gravitational dance. For centuries, people have wondered what worlds might orbit them. Imagine standing on a planet there, looking up at 2 suns in the sky, one slightly larger, one slightly smaller, casting overlapping shadows and double sunsets. If such a world exists, it would be both alien and strangely familiar at the same time. Beyond Alpha Centauri, the list of neighbours expands quickly. Barnard's star, a faint red dwarf 6 light-years away, moves rapidly across the sky compared to other stars. Wolf 359, another dim dwarf, lies not much farther. Sirius, the brightest star in our night sky, is 8 light-years distant, outshining almost every other neighbour because it is both large and close. To the naked eye, Sirius looks like a single point, but it is actually a binary system, with a massive main star and a faint white dwarf companion. That white dwarf is the burned-out remnant of a star that once shone brightly, now collapsed into a dense core the size of Earth, but with the mass of the Sun. To imagine such an object nearby is to see both the future and the past of stars in one system. Each of these neighbours lies only a few light-years away, but that phrase, only a few, is deceptive. 4 light-years is 40 trillion kilometres. 6 light-years is 60 trillion. These are distances so large that even beams of light take years to bridge them. Yet on the scale of the galaxy, they are close. If the Milky Way were shrunk to the size of a city, these nearby stars would be the houses on your street. The next cluster would be across town, and the far edges would be whole continents away. What makes meeting these neighbours so striking is the diversity among them. Some are hot blue giants, radiating so much energy that they will live only a few million years before exploding. Others are tiny, glowing faintly for trillions of years. Some are alone, wandering through space without companions. Others are part of binary or even triple systems, locked together in gravitational orbits. Some have planets large and small. Some may have none at all. Each one is its own solar system, its own experiment in how stars and worlds can form. Astronomers have only recently begun to glimpse those worlds. Using careful measurements of starlight, they can detect the wobble caused by orbiting planets, or the tiny dimming when a planet passes in front of its star. Already, thousands of exoplanets have been found, and among the nearest stars, planets are proving to be common. There are gas giants larger than Jupiter, small rocky worlds like Earth, super-Earths several times our size, and strange ones unlike anything in our system, hot Jupiters whirling close to their suns, or frozen giants orbiting far away. Meeting our stellar neighbours is not just about the stars themselves, but about the systems they carry. Imagine if you could visit one of them, perhaps a world around Proxima Centauri. You would stand on its surface under the dim red glow of its star. The light would be weaker than sunlight, tinted crimson. Days and nights might be strange, because many planets around red dwarfs orbit so close that they're tidally locked, one side always facing the star, the other side in eternal darkness. Life, if it exists, might cluster in the twilight zones, where the light is neither too strong nor too absent. Or imagine a planet around Alpha Centauri A or B, where two suns rise and set. Shadows would overlap, stretching and doubling. The rhythm of days would be complex. The warmth of two stars might change seasons in ways we cannot yet imagine. These possibilities stir not only curiosity but a sense of connection. When you realise that even our nearest neighbours have planets, the idea that life could exist elsewhere begins to feel less like speculation and more like probability. If the nearest stars have them, and the next stars too, and the next, then across hundreds of billions, the chances grow overwhelming. Meeting our stellar neighbours, even in thought, is also meeting the possibility of other lives. But even if no life exists there, the stars themselves are worth knowing. Sirius, shining blue-white, dazzling on winter nights. Procyon, part of the same neighbourhood. Epsilon Eridani, a young star with dust rings and hints of planets, only 10 light-years away. Each one is close enough that we can imagine visiting, close enough that their light is still young when it reaches us. The photons that strike your eye from Proxima Centauri began their journey 4 years ago, from Sirius 8 years ago, from Epsilon Eridani 10. These times are small compared to the age of the universe. They remind us that, in galactic terms, our neighbours are near enough for their stories to reach us almost immediately. The diversity also gives us a sense of the galaxy's richness. Our Sun is an ordinary star, mid-sized, mid-aged. Yet among our neighbours are remnants of old stars, newborns just igniting, pairs circling one another, giants that burn hot and fast. To meet them is to see that even the local neighbourhood holds every stage of stellar life. And just as our solar system has its outer reaches, each of these stars may be surrounded by belts, clouds, or unseen objects. The neighbourhood is not empty. It is full of suns, each with its own reach. If you could look around from a vantage point halfway between the Sun and Proxima Centauri, the sky would look different. The constellations would shift, their familiar shapes stretched and bent by the change in perspective. Orion, for instance, would no longer look like the hunter we know. Some stars would have shifted positions noticeably. Constellations are patterns seen from Earth, but they are not fixed. They are the product of our viewpoint. To stand among the stars is to see that their arrangements are illusions of distance, changing with every step outward. And beyond even these neighbours, more stars wait. Each step outward multiplies the number of suns until the sky is a dense scattering of them. The local neighbourhood extends for dozens of light years, a region filled with hundreds of stars. Some are brighter, some dimmer, but altogether they form the patch of galaxy we can call our own. Meeting them is only the beginning of seeing the Milky Way as a whole. So as we drift outward, past the fading influence of the Sun, past the emptiness between, and into the company of these other stars, we begin to understand the scale differently. We're not just one solar system in isolation. We are part of a stellar community, each neighbour close enough to touch us with light. Each one a reminder that the galaxy is not an abstraction, but a real crowded place filled with suns. When you look up at the night sky from a dark place, away from city lights, you might notice a faint band stretching across the heavens. It looks like spilled milk, hazy and delicate, broken by darker lanes where dust hides the glow. For thousands of years, people have given it names. a river, a pathway, the spine of the night. Today, we call it the Milky Way, and what you see in that faint band is not mist or cloud, but the combined light of billions of stars, each one too far and too faint to be seen alone, blending into a soft glow. That streak is our first direct glimpse of the shape of the galaxy we live in. At first, it seems strange to think we can know the galaxy's form when we're inside it. Imagine trying to see the shape of a forest while standing in the middle of the trees. From the ground, you cannot see the full pattern. You only see trunks rising around you. But if you study carefully, the density of trees in each direction, the way shadows fall, the distances between clearings, you can begin to infer the forest's outline. Astronomers did much the same. They mapped the positions of stars, counted them, measured their motions, and slowly realized that our galaxy has a structure. It is not a random scatter. It is a disk, broad and thin, with arms spiraling outward, all rotating around a central bulge of stars. The Milky Way is vast beyond simple numbers. Its diameter is about 100,000 light-years. If you could ride a beam of light from one edge to the other, it would take you 100,000 years to cross. Its thickness is about 1,000 light-years, like a pancake spread thin, with a central bulge that swells upward and downward. Within this disk are hundreds of billions of stars, along with gas, dust, and dark matter. We cannot see directly, but know must be there from the way gravity pulls. The spiral arms are perhaps its most beautiful feature. They are not rigid structures, not solid things. They are regions of higher density, waves moving through the disk where stars are more concentrated. As gas clouds drift into these arms, they are compressed, triggering new bursts of star formation. That is why spiral arms glow with young, hot blue stars and with the pink of glowing hydrogen nebulae. Between the arms, stars are older, dimmer, and fewer. The pattern is not fixed but dynamic, slowly changing over millions of years. Still, from afar, it would look like a graceful spiral, a glowing pinwheel turning in the dark. We cannot step outside to see this directly. Every image you've ever seen of a spiral galaxy from above is of another galaxy, not our own. But by studying those galaxies, and by measuring the stars around us, we have pieced together a portrait of what our home must look like. We live not in the centre, but out in one of the spiral arms, a smaller spur called the Orion Arm, located about halfway from the galactic centre to the edge. That's our address on the galactic scale, not at the hub, not at the rim, but comfortably in between. The central bulge is a dense, crowded region filled with stars. At its very heart lies something even stranger, a supermassive black hole, millions of times the mass of the Sun. It is called Sagittarius A-arm, hidden behind thick clouds of dust. We cannot see it with our eyes, but radio telescopes have traced its presence. Stars whip around it at incredible speeds, revealing a mass so great that nothing else could explain it. That black hole anchors the galaxy, holding the orbits of billions of stars, though it does not pull them like a drain. Instead, it is part of the balance, a gravitational centre around which the Milky Way turns. If you could see the galaxy from the outside, perhaps hovering above it in some impossible vantage point, it would be stunning. A flat disk of stars, glowing arms curling outward, a bright centre, and faint halos of stars surrounding it. Beyond the visible light, there would be the dark matter halo, invisible but massive, extending far beyond the stars we see. Without that halo, the galaxy's rotation would not make sense. The stars at the edges move faster than they should if only visible matter existed. Dark matter provides the missing mass, though what it is remains unknown. From our vantage inside the disk, we see the galaxy edge on. That is why the Milky Way appears as a band across the sky. We are looking along the plane of the disk, through layer upon layer of stars and dust. In directions away from the band, we look up or down out of the disk into regions where fewer stars lie. This explains why the night sky has a structure. crowded in one direction, sparse in others. Every night you have ever looked up, you have been seeing evidence of the galaxy's shape without knowing it. To appreciate the size of this structure, think again of light years. We spoke of our stellar neighbours as a handful of light years away. The galaxy is 100,000 light years across. That means there are not just a few stars nearby, but hundreds of billions stretching in every direction. So many that even with the most powerful telescopes we can never see them all individually. They merge into a background glow, the way distant lights in a city blur together into a haze. Our place in this galaxy is both ordinary and extraordinary. Ordinary because there is nothing particularly special about the Sun. It is a mid-sized star in a mid-sized arm, not near the centre, not on the edge. Extraordinary because this ordinary position allows us a stable environment, away from the chaos of the crowded core where supernovae and black holes would make life harder. From this quiet suburb of the Milky Way, life on Earth has flourished for billions of years. The galaxy is not static. It rotates slowly, taking about 200 million years for the Sun to complete one orbit around the centre. That means since Earth formed, the solar system has circled the galaxy more than 20 times. Every orbit, the sky above would have looked slightly different, as the stars around us shifted, arms approached and passed, and clouds of gas drifted by. The galaxy is alive with motion, even if it unfolds on timescales too long for us to notice. Meeting our stellar neighbours gave us a glimpse of the diversity of stars nearby. Seeing the galaxy's shape shows us the context of all of them. They are not scattered randomly. They are arranged in a structure, a grand spiral, a pattern of density waves and flowing motion. And this pattern is only one among countless others. Every spiral galaxy you see through a telescope is another city of stars like ours, another glowing wheel turning in the night. If you could hover outside and look back at the Milky Way, you would see not just beauty but scale. You would see that our solar system is one tiny dot in one of the arms, indistinguishable from the others. You would realise that all the stories of Earth, all of human history, all of life, are unfolding on a speck within this vast disk, and yet that speck is part of something immense, something luminous, something woven into the larger fabric of the cosmos. And from this perspective, it becomes natural to wonder, how many stars are there? How many lights fill this disk? How many suns lie waiting, each with their own worlds, their own possibilities? When you look up at the night sky and see a scattering of stars, it is tempting to imagine that what you see is even close to the true number. But in reality, your eyes are only catching the tiniest fraction. On the very best night, far from city lights, you might see a few thousand stars. That number sounds large until you compare it to the true population of the Milky Way, which is estimated to hold hundreds of billions. The gap between what we see and what is really there is almost beyond belief. Counting the stars of the Milky Way is not simply a matter of tallying them like coins in a jar. It is an exercise in measurement, inference, and imagination, because no one will ever count them one by one. Astronomers have long tried to estimate the number, using a mix of careful observation and clever reasoning. One way is to measure the total mass of the galaxy, and then estimate how much of that mass belongs to stars, compared to gas, dust, and dark matter. Divide that stellar mass by the average mass of a star, and you get a rough count. Another way is to count the stars in a small patch of the galaxy, a region where you can observe them more directly, and then scale up based on the size of the Milky Way as a whole. Neither method is perfect, but both converge on the idea that the Milky Way contains somewhere between 100 billion and 400 billion stars. That range alone tells you how hard it is to pin down. Even with all our technology, we can only narrow it to within hundreds of billions. But let's pause for a moment and think about what a billion really means. In everyday life, a billion is a number we hear but rarely grasp. 1,000 seconds is less than 20 minutes. 1,000,000 seconds is about 11.5 days. 1 billion seconds? That is over 31 years. When we talk about 100 billion stars, we're talking about a number so large that even breaking it into years of seconds still feels overwhelming. It is the kind of number that slips out of the fingers of comprehension, and yet we can build a sense of it through comparison. Imagine again that each star were a grain of sand. 100 billion grains would fill several large stadiums. 400 billion would cover entire beaches. Or picture the stars as people. The entire population of Earth is about 8 billion. The Milky Way holds 10 to 50 times that many suns. If every human being represented a star, you would need several dozen Earths to match the galaxy's population. Suddenly, the sky above you feels less like a scattered field, and more like a bustling city, crowded with lights. Of course, not all stars are the same. Some are giants, many times the mass of the sun, burning brightly but briefly. Others are dwarfs, small and dim, burning for trillions of years. Most of the stars in the galaxy are not like the sun. They are smaller, cooler, redder. Red dwarfs make up perhaps 3/4 of the Milky Way's population. They are faint, so faint that not a single one is visible to the naked eye, even though they surround us in every direction. That means that when you look at the sky, you're not seeing the majority. You're seeing only the brighter exceptions, the rare few that shine strongly enough to be noticed from Earth without a telescope. The true count is hidden, woven into the dark. And then there are the extremes. There are white dwarfs, the burned-out cores of stars that have finished their lives. There are neutron stars, collapsed remnants so dense that a teaspoon of their matter would outweigh a mountain. There are black holes, invisible but still counted in the tally of stellar remnants. All of these are part of the Milky Way's population. Counting stars means counting not only those that burn brightly today, but also those that once did, and those that will in the future. To add another layer, many of these stars are not alone. Roughly half belong to binary or multiple systems, pairs or trios orbiting around each other. To us they may look like a single point of light, but up close, they are families. Some circle each other closely, trading gas and energy. Others are separated by great distances, drifting together through their orbits like distant companions. Counting stars is not only about tallying individuals, but recognizing these systems as part of the whole. The number of stars also gives us a sense of how many planets may exist. With the discovery of exoplanets, we now know that planets are common. Almost every star likely has at least one. Many have several. If the Milky Way holds hundreds of billions of stars, then it likely holds hundreds of billions of planets, perhaps even trillions. Some are rocky, some are gaseous, some icy, some hot. The sheer abundance is staggering. The night sky is not just filled with stars, but with worlds, most of which we will never see directly. The true richness of the galaxy lies not only in its suns, but in the countless systems orbiting them. When you think about trying to count the stars, you realize quickly that the task is not only about numbers, but about scale. Imagine dividing the galaxy into patches, each one a square light year across. In our neighbourhood, there are only a handful of stars within that space, but closer to the galactic centre, the density rises. Stars crowd together more tightly, separated by only fractions of a light year. In globular clusters, ancient groups of stars orbiting the Milky Way, the density is even greater, thousands packed into small volumes. Counting the stars means recognizing that they are not evenly spread, but gathered and thinned, dense in some places, sparse in others. And then there is the halo, the faint population of stars orbiting far above and below the disk. These stars are older, dimmer, and harder to see, but they too belong to the count. They remind us that the galaxy is not only a disk, but a three-dimensional structure, filled with layers and components. What does it mean, really, to know that there are hundreds of billions of stars in the Milky Way? For one thing, it changes how we see ourselves. On Earth, we often think of our sun as central. It dominates our sky, our lives, our entire system. But in the context of the galaxy, It is just one among billions, unremarkable except for the fact that we live near it. It is one grain of sand on a vast beach, one light among countless others. This perspective can feel humbling, but it can also feel reassuring. The same laws of physics that govern our sun govern them all. The same processes that formed Earth's planets happen everywhere. We are not separate from the galaxy. We are an ordinary part of it. And yet, ordinary does not mean small in significance. For us, this single star is everything. It is the anchor of life, the source of energy, the centre of our local system. In the middle of the crowd, it is the one that matters most to us. That tension between being one of billions and being everything to us is part of the wonder of counting stars. Each one is someone else's sun. Each one may hold its own worlds. To another species somewhere across the galaxy, one of those countless faint points might be as precious as the sun is to us. When astronomers count stars, they also learn about the history of the galaxy. By measuring their ages, compositions and motions, they piece together a story of how the Milky Way formed. The oldest stars, low in heavy elements, date back to the early universe, when only hydrogen and helium existed. Younger stars contain more metals, forged in supernovae and spread across the galaxy. The mix of ages tells us that the Milky Way has been forming stars for billions of years and continues to form them today. Counting is not just tallying, it is reconstructing a timeline, seeing the galaxy not as a static structure, but as an evolving city of stars. Even now, with all our knowledge, the number remains approximate. We may never know the exact count, but perhaps that is fitting. A precise number might reduce the sense of immensity. To know instead that there are hundreds of billions, that they fill the disk and halo, that they stretch from the centre to the edge, is enough to remind us of the vastness of the place we live. When you next step outside and look up, remember that each star you see is only one of hundreds of billions, and that most of the stars are invisible to your eyes. The galaxy is not a scattering of points, but an ocean of light so vast that our senses can only catch a tiny spray from its waves. When we talk about the Milky Way, it is easy to focus on the stars alone. After all, they are what shine. They are what you see when you glance upward on a clear night. But stars are not the only inhabitants of the galaxy. Between them, around them, and after them exist other objects, stranger and sometimes more beautiful than we might expect. Black holes, nebulae, clusters, remnants. These fill the galaxy with variety. They remind us that the Milky Way is not only a city of stars, but a landscape of wonders. Black holes, for instance, are among the most mysterious residents. They are born from the collapse of massive stars, stars many times heavier than our sun. When such a star burns through its fuel, its core can no longer support the weight of its outer layers. Gravity takes over, crushing the core inward until nothing can resist. The result is a point so dense, so curved in its space-time that not even light can escape. That is the black hole, invisible by itself, yet revealed by its effects on the world around it. Our galaxy is thought to contain millions of stellar-mass black holes, scattered quietly through the disk. Most are dark and hidden, giving themselves away only when a companion star strays too close. In such cases, gas spirals inward, heating up and glowing with X-rays before vanishing beyond the event horizon. From Earth, astronomers detect these X-ray flashes, these sudden beacons in the dark, as evidence of a black hole feeding. They are not monsters hunting stars, but remnants of stars that lived and died long ago, continuing the cycle in a different form. At the very centre of the Milky Way lies a far larger one, Sagittarius A. This is a supermassive black hole, millions of times the mass of the Sun. For decades its presence was suspected, but only in recent years has its gravity been measured directly. Astronomers watched as stars near the centre whipped around something invisible, moving at thousands of kilometres per second. Only a mass so concentrated, so compact could explain it. And in 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A, a faint glowing ring of light surrounding a dark shadow, confirming what theory had long predicted. That image was not a picture in the everyday sense, but a reconstruction of radio waves collected across the planet, stitched together to reveal the shape of the unseeable. To know that such a thing exists at the core of our home galaxy is both unsettling and awe-inspiring. Yet the galaxy is not only defined by blackness, it is also filled with clouds of gas and dust, the raw material of stars glowing in colours invisible to the naked eye but revealed by telescopes. These are nebulae, and they are some of the most beautiful structures in the universe. Some are star-forming regions, vast nurseries where gravity pulls hydrogen together until fusion ignites. The Orion Nebula is one of the closest, a glowing patch visible with binoculars just below Orion's belt. Through telescopes, it appears as a swirl of pinks and purples, illuminated by young hot stars embedded inside it. This is where new suns are born, where new systems begin. Other nebulae are the remnants of dead stars. The Crab Nebula, for instance, is the aftermath of a supernova recorded by Chinese astronomers in the year 1054. For weeks, that explosion was visible in daylight. What remains now is an expanding cloud of gas and filaments, glowing from the energy of a neutron star at its heart. To look at it is to see the life cycle of stars made visible, death transformed into beauty. Planetary nebulae are another form, the glowing shells of gas shed by dying sun-like stars. Despite their name, they have nothing to do with planets. The early astronomers who named them simply thought they looked round and planet-like through small telescopes. In reality, they are the last breath of a star like ours, outer layers cast into space, shining from the heat of the fading core within. These delicate structures come in every shape imaginable. Rings, butterflies, hourglasses, sculpted by winds, magnetism, and chance. They last only tens of thousands of years, a brief moment in cosmic time before fading into the interstellar medium. Between these clouds, star clusters also dot the Milky Way. Open clusters, like the Pleiades, are groups of young stars born together from a single cloud, still drifting as a family before scattering across the galaxy. They are bright, tight groups, easy to spot in the night sky. Globular clusters, by contrast, are ancient spherical collections of hundreds of thousands of stars orbiting in the halo of the galaxy. They are older than most of the stars in the disk, fossils of an earlier age, still glowing after billions of years. To look at one is to peer back into the early days of the Milky Way, long before Earth had formed. All of these wonders, black holes, nebulae, clusters, remind us that the galaxy is alive with processes. Stars are born, they live, they die, and their remnants shape the space around them. Gas clouds collapse into new generations. Explosions scatter heavy elements. Clusters hold together or dissolve. Black holes pull and bend space-time itself. The Milky Way is not a static collection of stars frozen in place, but a dynamic system, constantly evolving, constantly recycling. When you step outside on a quiet night and look up, you do not see these wonders directly. You see only the stars, but through telescopes, through careful observation across the spectrum of light, radio, infrared, ultraviolet, X-rays. Astronomers have revealed this hidden side of the galaxy. What looks like empty space often glows brightly at other wavelengths. Dust that blocks starlight shines in the infrared. Black holes invisible in visible light blaze in X-rays. The universe is richer than our eyes alone can reveal, and perhaps that is the most striking part. Our galaxy holds not just stars, but phenomena so extreme they stretch our understanding. Black holes where gravity is absolute. Nebulae where stars are born or die. Clusters that preserve the memory of billions of years. Each is a reminder that the Milky Way is not just large, not just filled with stars, but also filled with variety, with drama, with beauty that comes from processes too vast and too long-lived for us to witness in their entirety. When you step back and take in the Milky Way as more than the sum of its stars and wonders, you realise that what surrounds us is not just a city of suns, but an ocean. It is an ocean so vast that even light, the fastest traveller we know, takes tens of thousands of years to cross it. To imagine such a journey is to try and sail across something that makes every earthly sea seem like a puddle in comparison. This is what it means to cross the galactic sea. Our solar system sits about halfway between the centre of the Milky Way and its outer edge, nestled within a smaller spur of one of the spiral arms. From here, the galaxy stretches outward in all directions, a disk of 100,000 light-years across. If you could rise above it and look down, you would see a glowing pinwheel, a spiral of light and dust. But from inside, what we experience is the long journey across its width, a sea where every star is an island, every nebula a lighthouse, and every cluster a port along the way. To cross such a sea, even in thought, means accepting distances that strain imagination. Our nearest star, Proxima Centauri, is 4 light-years away. That is like the first buoy just beyond the shore. The rest of the galaxy stretches 100,000 of those units. If you tried to compare it to earthly travel, you would fail immediately. Driving across a continent feels long. Flying across oceans feels long, but those are hours or days. To cross the galaxy would take 100,000 years, even at the speed of light. The scale makes human travel feel like the flapping of wings inside a cathedral. And yet the sea is not empty. Along the way are stars of every kind. The bright, massive blue giants that burn hot and fast. The small, cool red dwarfs that flicker for trillions of years. White dwarfs and neutron stars, remnants of explosions drifting like wreckage. Planetary systems are scattered everywhere, some familiar in form, others entirely alien. Crossing the galactic sea would mean passing by them one after another, each a world of its own, each a story of formation and change. Imagine setting out from our sun and heading toward the centre. At first the stars would thin, the gaps of interstellar space wide and dark. But the closer you drew to the heart of the galaxy, the more crowded they would become. Near the core, stars are packed so densely that if you lived on a planet there, the night sky would blaze with dozens of bright suns. The sky would never be dark. Instead, it would glow with light from every direction. Between those stars, massive black holes lurk, pulling at the fabric of space, bending paths, distorting light. It would be like sailing into a storm where gravity itself becomes turbulent. If instead you sailed outward toward the rim, the opposite would happen. The stars would thin and fade until only sparse outposts remained. Beyond the disk, you would rise into the halo where old, dim stars and globular clusters orbit quietly. From there, you could look back at the Milky Way itself, finally seeing it as a glowing spiral across the dark. Crossing outward feels like leaving the busy ports of a city and heading into a quiet, endless sea. One of the curious things about the galactic sea is how structured it is. The spiral arms are not physical ropes tying stars together, but density waves, places where stars and gas are more concentrated. As you move through them, you would encounter bursts of star formation. Young stars, bright and hot, would light the way. Gas clouds would glow, nebulae would bloom. Then, as you passed into the spaces between arms, things would grow quieter, stars older, light dimmer. It would be like moving from bustling islands to calm stretches of open water. Over millions of years, stars orbit the centre, arms shift, new structures form. The sea is never still. Crossing also reveals the scale of time. The sun itself takes about 200 million years to complete one orbit of the galaxy. That means in the 4.5 billion years since Earth formed, our solar system has circled the galaxy more than 20 times. Every orbit carries us through arms and between them, past dense regions and sparse ones. Civilizations rise and fall, continents form and drift, species evolve and vanish, all while the sun sails on, carrying us through the galactic sea without pause. It is humbling to think that the sky we see is temporary. The constellations that look so familiar are just arrangements from our current position. As the sun continues its orbit, the patterns will shift. Stars will move relative to us, some fading, some brightening, some replaced by newcomers. 100 million years from now, the sky will be unrecognizable. The galactic sea is not a frozen map. It is a current, carrying us through a changing landscape of stars. Even the most distant places in this sea are part of the same whole. Globular clusters, dense swarms of ancient stars orbit far above and below the disk. Some contain hundreds of thousands of suns, packed tightly together. These clusters are like floating islands in the halo, reminders of the galaxy's early days. Their stars are older than the sun, older than Earth, older than life itself. To visit one would be to look into the past, to see the galaxy as it was billions of years ago. Then there are the streams, rivers of stars that trace across the halo, remnants of smaller galaxies torn apart by the Milky Way's gravity. They weave like trails of debris, evidence of the galaxy's growth. Because the Milky Way has not always been as it is now. Over billions of years it has absorbed smaller galaxies, pulling them in, mixing their stars with its own. To cross the galactic sea is to see not only stars but history written in their motions, in their chemical fingerprints, in the way they orbit. The sea is also dark in ways we cannot see directly. The stars, nebulae and clusters are only the visible part. Beneath them, surrounding them, lies dark matter. It does not glow, it does not absorb light, but its gravity shapes the galaxy. Without it, the outer stars would drift away. With it, they are held in orbit. Astronomers can only detect dark matter through its influence, but they estimate it makes up most of the galaxy's mass. Crossing the galactic sea, you would not see it, but you would feel its pull, silent and invisible, holding everything together. And then there is the perspective from within. From Earth, we see the Milky Way as a faint band, because we are inside the disk looking along it. From another vantage we would see it edge on, a thin streak of light across the dark. From above, we would see the spiral arms unfolding like petals. Each viewpoint changes the sense of scale, but no matter the angle, the Milky Way remains immense. Crossing it is not something any being could do in a lifetime. It is a journey of thought, of imagination, carried by light itself. Perhaps the most striking realization is that we are always crossing. Every moment the sun carries us forward. We do not feel it, but we are moving at hundreds of kilometers per second, orbiting the galactic center, threading our way through the arms. The Earth turns, the solar system drifts, the galaxy itself rotates. The sea is not one to cross only once. It is one we are sailing through always, whether we notice or not. When you step back from the Milky Way and think of it not as the whole of everything, but as one part of a larger gathering, a new layer of scale comes into view. Our galaxy, immense as it feels, is not solitary. It belongs to a family, a group of galaxies bound together by gravity, drifting through space as companions. Astronomers call it the local group. The name sounds simple, almost casual, as if you were talking about a neighborhood association, but in reality it refers to a collection of dozens of galaxies spanning millions of light years, moving in relation to one another, sharing a common destiny. The local group is centered on two giants, the Milky Way and the Andromeda Galaxy. These are the two largest members, each with hundreds of billions of stars. Andromeda, also known as M31, is slightly bigger than our galaxy, stretching about 250,000 light-years across. From Earth, it appears as a faint smudge of light in the constellation Andromeda, just visible to the naked eye under dark skies. That faint smudge is the light of 1 trillion stars combined, travelling more than 2 million years to reach us. To see Andromeda is to look across space and time, catching sight of our closest large neighbour. Between the Milky Way and Andromeda lies a dance. The two galaxies are moving toward each other, and in about 4 billion years they will collide. The word collision sounds violent, but in galactic terms it will be more like an interweaving. The stars are so far apart that very few will strike directly. Instead, the galaxies will pass through one another, their shapes distorted, their arms stretched, their stars flung into new orbits. Over time, they will merge into a single larger galaxy, sometimes nicknamed Milky Way. To think of this is to realize that even galaxies are not permanent. They live, move, and change, just like stars and planets. The local group is not frozen. It is alive with motion. Beyond these two giants are smaller members. The Triangulum Galaxy, or M33, is the third largest, though far smaller than the other two. It is a spiral as well, delicate and rich with star formation, shining with clusters and nebulae. Then there are the dwarf galaxies, dozens of them, scattered around the larger ones like satellites. The Milky Way itself is orbited by many dwarfs. The large and small Magellanic Clouds, visible from the southern hemisphere as irregular glowing patches, are the most prominent. They're galaxies in their own right, each with billions of stars, but compared to the Milky Way they're tiny, like children trailing alongside a parent. Other dwarves are fainter still, so dim that they were only discovered recently. Some are stretched and distorted by the Milky Way's gravity, remnants of larger galaxies being absorbed into ours. This is one of the striking things about the local group. It is not a static collection, but a dynamic, evolving system. Galaxies fall into one another's gravity, orbit, merge, or dissolve. The Milky Way has consumed many smaller galaxies over time, their stars now mixed into our halo. Streams of stars, long ribbons stretching across the sky, are the evidence of these ancient meals. The local group is a place of interactions, not isolation. In terms of size, the local group stretches about 10 million light-years across. That number is hard to imagine, but it means that light, travelling at 300,000 kilometers per second, takes 10 million years to cross from one side to the other. The galaxies within are spread across this vast region, like islands in an archipelago. Some are close together, like the Milky Way and its dwarves. Others are farther apart, drifting on the outskirts, yet all of them are bound by gravity into a shared system. If you could look at the local group from the outside, you would see the Milky Way and Andromeda as the dominant spirals, Triangulum as a smaller but still noticeable spiral nearby, and then dozens of faint smudges surrounding them. It would not look crowded, but scattered. Galaxies are immense, but they are also separated by enormous gulfs of space. Between the Milky Way and Andromeda, there are over 2 million light-years of emptiness, filled only with the thin gas of intergalactic space. The local group is a community, but a spread-out one. Still, that community matters, because it is the structure we belong to. Just as our solar system is part of the Milky Way is part of the local group. It is our cosmic address, the next step in scale, and within this group, interactions shape the future. The eventual merging of the Milky Way and Andromeda will reshape everything. New waves of star formation will light up as gas clouds collide. Stars will be flung into new orbits. The shape of the galaxies will change. For billions of years afterward, the local group will look different than it does now. The slow unfolding of this process is beyond human time, but it is part of the fabric of cosmic history. The smaller galaxies are no less interesting for being small. Some are irregular, without clear structure, shaped by gravitational tides. Others are spheroidal, faint and diffuse, barely holding together. Many are poor in gas and dust, having lost their raw material for star formation long ago. They are fossils of earlier times, survivors of a more crowded past. Studying them gives astronomers clues about how galaxies form and evolve. Each one is a laboratory of cosmic processes, even if it looks like a faint blur in a telescope. the local group is also defined by what lies beyond. It is not isolated in the universe, but part of an even larger structure. The Virgo supercluster, a vast gathering of groups like ours, bound together into an even greater whole. But before we reach that, it helps to sit for a while with the idea of this group alone, because already the scale has grown from stars to galaxies, from light years to millions of light years. Already we are looking at dozens of immense systems instead of one. The Milky Way is no longer the largest horizon. It is one of many, each shining across space, each carrying billions of suns. What makes the local group so fascinating is the balance it holds. On the one hand, it is small compared to the universe. There are clusters of galaxies far larger, with hundreds or thousands of members. On the other hand, it is vast compared to our galaxy alone. 10 million light-years is already beyond the reach of our imagination. Yet it is close enough that we can map it in detail, measure distances, trace orbits, and even see the faintest dwarfs. It is local not because it is small, but because it is the space around us that we can grasp. When you look up and see Andromeda, faint and hazy, you are seeing across that gulf to the next great island of stars. You are seeing part of the local group with your own eyes. It is not only an idea in astronomy textbooks, but a real, visible thing. That connection between what you can see and what science describes is part of the wonder. The faint smear in the night sky is not just a blur. It is another galaxy, another city of stars moving toward us, bound together with us in the same group. Once you take a step back from the local group, something remarkable begins to happen. The galaxies that seemed so spread out with millions of light years between them start to look closer again because the scale has shifted. Now you're no longer thinking about single galaxies or even small groups of them. You're seeing the larger gatherings, where dozens or even hundreds of galaxies are bound together by gravity, forming clusters. And when those clusters themselves are arranged into still larger patterns, connected by filaments and threads, you have superclusters, some of the grandest structures known in the universe. A galaxy cluster is not like a family of galaxies such as the local group. It is much bigger, much denser, and often far more dramatic. The Virgo cluster, for example, is the nearest large cluster to us. It lies about 50 million light-years away and contains over 1,000 galaxies. Imagine that. Not a dozen or two, but thousands of vast spiral and elliptical galaxies, each with hundreds of billions of stars, all bound together in a gravitational knot. When you look at the constellation Virgo through a telescope, many of the faint smudges you see are galaxies belonging to this cluster. It is so massive that the local group itself is drifting slowly toward it, drawn by its gravity, though the journey will take billions of years. Clusters are not gentle places. They're crowded with galaxies that sometimes collide, merge, or distort each other with tidal forces. When two galaxies crash together, their stars almost never collide directly, because the stars are too far apart. But their gas clouds do, compressing and igniting new waves of star formation. Their shapes are pulled and stretched, arms twisted, cores disrupted. Over time, clusters evolve, smaller galaxies merging into larger ones. The result is that many clusters are dominated by giant elliptical galaxies at their centres, the outcomes of countless mergers. These central giants can be hundreds of thousands of light-years across, far larger than the Milky Way, glowing with the combined light of trillions of stars. And between the galaxies and clusters lies not emptiness, but something unexpected. Vast amounts of hot, thin gas. This intracluster medium, as it's called, is heated to millions of degrees, glowing in X-rays. Though invisible to our eyes, it actually makes up more mass than the galaxies themselves. To cross a galaxy cluster is not to pass through darkness, but through a sea of hot plasma, stirred by gravity and turbulence. The gas is enriched with elements from countless supernovae, spread outward over billions of years. It is the breath of galaxies, filling the space between them. Clusters also contain something else: dark matter. Just as in individual galaxies, the visible matter is not enough to explain the gravity that holds clusters together. The galaxies move too fast. The gas glows too brightly from its heat, which would escape unless something unseen kept it bound. That something is dark matter, again outweighing everything we can see. Clusters, then, are not just gatherings of galaxies. They are evidence of the invisible scaffolding of the universe, the skeleton of dark matter around which light and matter arrange themselves. If clusters are the neighborhoods of the cosmos, then superclusters are the cities. A supercluster is a collection of many clusters, linked together across hundreds of millions of light years. Our local group is part of the Virgo supercluster, which itself is only a small piece of an even larger structure called the Laniakea supercluster. Laniakea is immense, spanning over 500 million light years and containing about 100,000 galaxies. It is so vast that even light, travelling at cosmic speed, would take 500 million years to cross it. That's longer than complex life has existed on Earth. The name Laniakea comes from Hawaiian, meaning immense heaven, and it is fitting. Imagine looking at the universe not galaxy by galaxy, not cluster by cluster, but in terms of flows. Galaxies are not static. They move, carried by the pull of gravity. By mapping these flows, astronomers discovered that the Milky Way, the local group, and even the Virgo cluster are all moving toward the same region of space, a gravitational basin known as the Great Attractor. This region lies at the center of Laniakea, where the mass of tens of thousands of galaxies bends the paths of everything nearby. It is less like a place and more like a gravitational current, a sink in the cosmic sea. To belong to Laniakea is to be carried within that current, along with all the galaxies around us. It is here that the sense of scale truly begins to overwhelm. Think again of light years. The local group stretched across about 10 million. The Virgo cluster is tens of millions away. Laniakea stretches 500 million. Each step is an order of magnitude larger, another leap beyond the mind's usual comfort zone. And yet these are real structures, mapped and measured, not abstractions. Clusters and superclusters are the way matter organizes itself on the larger scales. If you could hover outside a supercluster and look back, you would not see a single glowing shape, like you see with a galaxy. You would see a loose scattering of galaxies and clusters, strung along filaments, connected in patterns. It would not look crowded, but surprisingly delicate, like lace or a web. This is because even a supercluster is mostly empty space. The galaxies are tiny compared to the distances between them, but from a distance the pattern emerges, a structure so vast it defies direct experience. And these structures are not fixed forever. Over time, cosmic expansion stretches the space between them. Galaxies not bound by gravity to one another drift apart, carried by the expansion of the universe. Superclusters themselves may someday fragment, their members carried away beyond the reach of light. But for now, in our cosmic time, they exist, and we can see them. We can map them, name them, trace their edges. The existence of clusters and superclusters also reminds us of how matter in the universe clumped together in the first place. After the Big Bang, matter was almost evenly spread. Tiny fluctuations in density, slightly denser here, slightly thinner there, grew over time as gravity pulled more matter into the dense spots. Those became galaxies. Galaxies gathered into groups, groups into clusters, clusters into superclusters. The structures we see today are the grown-up forms of those infant ripples in the early universe. Counting clusters is, in a way, reading the after effects of the beginning itself. And even here, even at these scales, we're not at the largest. Because superclusters themselves are not isolated islands. They are part of an even greater pattern, the cosmic web, where filaments of galaxies stretch across billions of light years, separated by enormous voids of almost nothing. But before we step that far outward, it is worth lingering on the idea of clusters and superclusters themselves, because they are the first hint that galaxies are not the end of structure, but part of something larger. Imagine yourself drifting among them. You pass the Milky Way, you move beyond the local group, you see Andromeda and Triangulum falling behind. Ahead, the Virgo cluster begins to rise, its galaxies glowing in every direction. Thousands of them, each as vast as the Milky Way, filling your vision. Beyond that, the clusters stretch on, linked by threads into the larger whole. You realise that the sky is not just filled with stars or galaxies. It is filled with structures, immense and interconnected, too large for any one lifetime to cross, but visible, knowable, describable through the patience of science. As you move beyond superclusters, you begin to see that even those immense gatherings are not the largest picture. There is another layer, a pattern stretching across billions of light years, a kind of architecture that reveals itself only when you look at the universe as a whole. Astronomers call it the cosmic web. It is the grandest structure we know, the way matter arranges itself on the largest scales, a vast network of filaments, clusters and voids, woven together like threads of light stretched across the dark. The cosmic web was not obvious until recently. For centuries, the night sky seemed like a scattering of stars. Even after telescopes revealed galaxies, those galaxies still seemed randomly placed. But as astronomers mapped more and more of them, surveying their positions in 3 dimensions, a pattern began to emerge. Galaxies were not evenly distributed. They were not sprinkled uniformly like sugar across a table. Instead, they gathered into long chains and sheets, with enormous empty regions between them. These empty spaces, called voids, can span hundreds of millions of light years, almost entirely devoid of galaxies. Between them, the galaxies form filaments, narrow highways of matter where gravity has drawn them together. When you step back far enough, what you see looks like a web, intricate and interconnected, spanning the universe itself. Imagine zooming out from the local group. First, you see the Virgo supercluster, then Laniakea stretching 500 million light years. But as you go farther, you notice that Laniakea is just one strand among many. Other superclusters lie nearby, connected by filaments, separated by voids. Together, they form something larger, something like a spider's web stretched across space. If you could look down on it from above, it would not look like a uniform fog, but like lace, delicate and patterned. The filaments glow faintly with galaxies, while the voids sit almost empty, vast dark bubbles where almost nothing resides. The web itself formed from the earliest moments of the universe. After the Big Bang, matter was nearly evenly spread, but not perfectly. There were tiny fluctuations, places where the density was slightly higher or lower. Over billions of years, gravity amplified those differences. The denser regions pulled in more matter, growing into filaments and clusters. The emptier regions lost matter, becoming voids. The result, after nearly 14 billion years, is this enormous web. In some ways, the pattern was already written in the very beginning, encoded in the faint ripples of temperature left behind in the cosmic microwave background. What we see now is that initial blueprint stretched into its adult form. The filaments are not thin in human terms. They can be hundreds of millions of light years long and tens of millions wide. Within them are galaxies, clusters, superclusters, and vast amounts of dark matter. Gas flows along them, feeding the growth of galaxies. They are the highways of cosmic evolution, the places where structure forms and continues to grow. The voids, by contrast, are quiet and nearly empty, vast expanses where galaxies are rare. They are the deserts between the filaments, the spaces where little happens, reminders of the unevenness of the universe's design. What is striking is how familiar the pattern looks, even though the scale is unimaginable. Images of the cosmic web resemble networks we know. Neurons in the brain, filaments of fungi and soil, the branching of trees. Of course, these resemblances are analogies, not identities, but they remind us that patterns emerge across scales. Nature, it seems, favours networks. Whether in the microscopic world of biology or the macroscopic world of the universe, connections weave into webs. It gives us strange comfort to think that the largest structure we know shares a resemblance to the structures within us. If you were somehow able to drift through the cosmic web, you would spend most of your time in darkness. The filaments, for all their length and density, are still separated by enormous stretches of void. Travelling from one filament to another would take longer than the history of life on Earth, but along the way you would pass through regions where galaxies crowd more tightly, where clusters blaze with X-rays from hot gas, where new stars light up in nebulae. It would be like sailing between continents across an ocean, long stretches of emptiness broken by vibrant shores. The cosmic web also reminds us that even the largest structures are temporary. The universe is expanding, and with time, galaxies not bound by gravity will drift apart, carried beyond one another's horizons. Over billions and trillions of years, the web will thin, the filaments will stretch, the voids will grow. From our perspective now, we can still see the web in its fullness. We can still map the filaments and trace the flows. But in the far future, distant civilizations may not be able to see it at all. The expansion will carry most of the web beyond view. What feels like permanent structure now is, in cosmic terms, a phase. And yet, the web is our context. When we talk about the Milky Way, the local group, or the Virgo cluster, we are talking about threads of this larger fabric. Our home is not just a galaxy or a group of galaxies. It is one node in a network stretching across the universe. To know this is to shift perspective once again. First Earth, then the solar system, then the Milky Way, then the local group, then superclusters, and now the cosmic web. Each step outward reveals a larger whole, until finally we're looking at the universe itself as a patterned structure. When astronomers create maps of the cosmic web, they often show it glowing with false colours, filaments lit in blues or yellows, voids dark. These are not what the universe looks like to our eyes, but they are accurate in shape. And even in those maps, the sheer emptiness dominates. Most of the universe is void. The galaxies, the filaments, the stars, they are the rare structures, the exceptions in an otherwise dark expanse. The cosmic web is delicate not because it is weak, but because it is sparse, a lace of light stretched across vast emptiness. But sparse does not mean unimportant. It is along the filaments that galaxies form, where stars ignite, where planets and perhaps life emerge. The web is the stage upon which everything we know plays out. To live within it is to be part of a network so large we cannot traverse it, but so structured we can recognize its shape. Imagine looking at it from outside, if such a thing were possible. You would see billions of light years across, filaments glowing faintly, clusters brightening the knots where threads meet, voids spreading like great dark bubbles. You would see the largest architecture known, a universe not random but patterned, shaped by gravity, born from fluctuations nearly 14 billion years ago. And you would realize that the place you occupy, the galaxy you call home, is just one tiny dot along one of those filaments, a single bead on a thread stretching across eternity. And still, the web is not the limit. Even after mapping these filaments and voids, there is another question waiting. How many of them are there? How many galaxies in total fill this web? When we speak of stars, the numbers already feel overwhelming. Hundreds of billions in the Milky Way alone. But when you step out to the scale of galaxies, the count expands into something even harder to hold. It is one thing to know that each galaxy is a city of stars. It is another to realize just how many of those cities exist. Counting the galaxies is not a simple task, not even close. It is a project that stretches our instruments, our mathematics, and our imagination, because the true number is so far beyond anything we encounter in daily life. For a long time, astronomers had no real sense of the number, Before telescopes, the Milky Way itself was thought to be the entire universe. The faint smudges in the sky, like Andromeda, were mysterious. Nebulae, perhaps clouds of gas. It was only in the early 20th century that astronomers realised those smudges were not clouds within our galaxy, but entire galaxies of their own, as large or larger than the Milky Way, each holding billions of stars. The scale of the universe expanded in an instant. What had looked like a foggy patch in the night was actually a vast spiral 2 million light-years away. As telescopes grew more powerful, the faint patches multiplied. The Hubble Space Telescope, launched in 1990, offered one of the clearest glimpses. Astronomers pointed it at what looked like an empty piece of sky, a patch no larger than the tip of a pin held at arm's length, and let it gather light for days. The result was the Hubble Deep Field, an image filled not with emptiness but with thousands of galaxies, each one a unique shape, each one a distant island of stars. The lesson was immediate and profound. If a tiny corner of sky contained thousands of galaxies, then the whole sky must contain hundreds of billions. Current estimates suggest that the observable universe contains at least 2 trillion galaxies. 2 trillion. Numbers that high often slide past comprehension, but let's try to anchor it. 1 million seconds is about 11.5 days. 1 billion seconds is about 31 years. 1 trillion seconds is over 31,000 years. 2 trillion galaxies means 2 trillion cities of stars, each with billions of suns. Multiply stars per galaxy by galaxies per universe, and you reach a number so large it makes every grain of sand on Earth feel like a small collection. That comparison has often been made. There are more stars in the universe than grains of sand on all the beaches of our planet. To count them all, even at 1 per second, would take longer than the age of the universe itself. And yet, counting is not hopeless. It is not about ticking off galaxies one by one, but about measuring the light. Astronomers gather the faint glow from distant space, measure its intensity, and use it to infer how many galaxies must exist to produce it. They use surveys like the Sloan Digital Sky Survey, which maps millions of galaxies across large portions of the sky, then extrapolate. They use deep images, like those from Hubble, or now the James Webb Space Telescope, which reveal galaxies too faint or too far for earlier instruments. Each advance pushes the estimate higher, showing us that the universe is richer than we thought. The diversity of galaxies adds another layer. Not all are spirals like the Milky Way or Andromeda. Many are ellipticals, vast round collections of old stars, smooth and featureless, often formed from mergers. Others are irregular, twisted or shattered by gravitational interactions. Some are tiny dwarfs, holding only millions of stars. Others are giants, with trillions. Counting galaxies is not just tallying numbers, but recognizing that each one is different, shaped by history, collision, and time. The most distant galaxies push the limits of what we can see. Their light has travelled for over 13 billion years to reach us, meaning we see them as they were when the universe was young. They are small, irregular, often bursting with new star formation. They remind us that galaxies, like stars, have lifetimes. They grow, merge, evolve. The spirals and ellipticals we see today were once smaller fragments. Counting galaxies is also counting their stages, a census not only of quantity but of age. 2 trillion is the number within the observable universe, the part of the cosmos from which light has had time to reach us since the beginning. Beyond that, we do not know. The universe may be infinite. If it is, then the true number of galaxies is uncountable. The observable horizon is not a wall but a limit defined by time and light. Beyond it, there may be more galaxies stretching forever. Our count is not the whole, only the part we can see. Still, even that part is staggering. Imagine standing on a beach at night, the waves rolling in, the sand cool beneath your feet. You bend down, scoop a handful of sand, let the grains slip through your fingers. Each grain could be a galaxy. Then imagine the whole beach, then every beach on Earth. Even then, you have only a fraction of the stars within those galaxies. The numbers are so large that they stop being numbers and start being metaphors. They become ways of pointing at immensity. What is perhaps most humbling is how recent this knowledge is. A century ago, humanity did not know there were other galaxies at all. The universe was thought to be only the Milky Way. Today, we speak of trillions. The expansion of perspective in such a short time is astonishing. It reminds us that the cosmos is not just large, but larger than we ever thought possible, and that each new tool we build, each new telescope reveals more. Counting the galaxies also raises questions. If there are so many, how many might host life? How many might hold civilizations wondering the same things we do? Even if life is rare, the sheer number of galaxies makes it almost inevitable that it exists somewhere else. The universe is not just immense in distance, but in possibility. Each galaxy is a canvas where stars burn, planets form, chemistry unfolds. To count them is to count opportunities for existence itself, and yet, from Earth, we see only hints. The Andromeda Galaxy is a faint blur, a few others visible with binoculars or telescopes. The rest are too distant, too faint, revealed only by long exposures and careful mapping. The night sky, which feels so full, is in reality only the thinnest layer of what is truly there. The stars above are local. The galaxies beyond are countless. When you let this sink in, it changes how you look at the sky. No longer do you see only points of light, but you realize that behind them, beneath them, across the blackness, there are layers upon layers of worlds stacked beyond sight. Counting the galaxies is not just about tallying. It is about realizing that the cosmos is deeper than our eyes can see, richer than our minds can easily hold. And even this, astonishing as it is still part of a larger picture, because the galaxies are not scattered alone. They are woven into filaments, connected in the cosmic web, expanding outward with the universe itself. And the question then arises, what is the size of all of this? What is the scale of the observable universe, and how do we begin to describe it? When you stand outside on a dark night and look up, it feels as though the sky stretches forever. The stars give the impression of infinity, a dome with no edge, a view without limit. But in reality, there is an edge. Not a physical wall, not a barrier you could ever touch, but a boundary set by light and time. The universe has existed for a finite age, nearly 14 billion years, and light travels at a finite speed. That means there is a maximum distance we can see. The distance light has had time to reach us since the beginning. This is what astronomers call the observable universe. Beyond it, the cosmos may continue, perhaps endlessly, but it lies forever hidden from our eyes, because the light from those places has not yet arrived, and may never arrive. The edge of what we can see is not measured in kilometers or miles, because those units collapse under such magnitude. It is measured in light years, billions upon billions of them. The farthest galaxies we have detected lie over 13 billion light years away, their light beginning its journey when the universe was young. But because the universe has been expanding during all that time, the distance to those galaxies today is far greater, about 46 billion light years, in every direction. That is the current radius of the observable universe. Put together, the whole sphere is about 93 billion light years across. That is the size of the bubble of visibility, the cosmic horizon that surrounds us. It is important to understand what that horizon means. It does not mean the universe ends there. It does not mean space stops. It simply means that beyond that distance, the light has not had enough time to reach us. Imagine standing in a foggy field with a lantern. The glow only extends so far. Beyond it, the fog continues, but you cannot see it. The observable universe is our lantern's glow, set not by fog, but by time. The faintest light we can detect from this edge is not starlight, but something older. It is the cosmic microwave background, the afterglow of the Big Bang itself. Nearly 14 billion years ago, when the universe was just 380,000 years old, it cooled enough for atoms to form, allowing light to travel freely for the first time. That light has been streaming across space ever since, stretched into microwaves by the expansion of the cosmos, now filling the sky in every direction. When we measure it, we're looking at the universe's surface of last scattering, the oldest light we can ever see. Beyond that point, the universe was opaque, filled with plasma, and no light could escape. The microwave background is therefore the true wall of vision, the edge of sight, the limit of our gaze. The concept of an observable universe is both humbling and strange. On one hand, it sets a boundary. No matter how powerful our telescopes become, we cannot see beyond it. The edge is not technological but fundamental, written into the laws of physics. On the other hand, the universe beyond that edge may be much larger, perhaps infinite. The observable universe is simply our portion, our bubble, the patch of cosmos we can access. Like standing on an island surrounded by ocean, we see only to the horizon, but we know the sea continues. To picture this horizon, imagine Earth at the centre of a sphere. Not because we are special, but because the horizon is defined relative to us. Every observer anywhere in the universe would see their own sphere centred on them. If you lived in a galaxy billions of light years away, you would also see a bubble of visibility stretching 46 billion light years in every direction. Our horizon is not unique. It is just our perspective. The cosmos offers each observer their own view, their own edge. Within this bubble lie all the galaxies, clusters and filaments we have spoken of. The cosmic web stretches across it, filling the observable universe with structure. Yet even within, the farther you look, the farther back in time you're seeing. Light takes time to travel, so looking at a galaxy 10 billion light years away shows you the galaxy as it was 10 billion years ago. The edge of what we can see is not only spatial but temporal. It is a limit in both distance and age. To look outward is to look backward, until finally you reach the microwave background and the faint glow of the beginning itself. What lies beyond the edge is one of the deepest questions in cosmology. The universe may extend infinitely, or it may curve back on itself in ways we cannot detect. It may contain regions with different structures, perhaps even different physical constants. But all of this remains speculation, because no information can cross the horizon. The expansion of space ensures that some parts of the universe are receding from us faster than light, not because they are moving through space, but because space itself is stretching. Their light will never reach us. They are forever outside our view. To think of this is to feel both small and privileged. Small, because we see only a fraction of the whole. Privileged, because we can see as much as we do. 93 billion light years across is not small. It is enormous, larger than anything we can directly grasp. That we can map even a fraction of it is astonishing. Astronomers have turned this concept into maps. They plot galaxies across the sky, measure their distances, trace the structure of the cosmic web within the horizon. These maps are always incomplete, because the farther you go, the fainter things become. Some galaxies are simply too far or too dim for us to detect. The count of 2 trillion galaxies in the observable universe is itself an estimate, a lower bound. The true number may be greater. Every new telescope pushes that estimate upward. One of the strangest consequences of the cosmic horizon is that we live in a kind of bubble of time. Galaxies near the edge may not even exist anymore as we see them. Their light began its journey billions of years ago. In that time, stars may have burned out, new ones may have formed, galaxies may have collided or changed shape. The image we see is a snapshot of the past, frozen and delayed. The universe we observe is not the universe as it is today, but as it was. The edge of sight is also the edge of the present. Even within this bubble, there are mysteries. Dark matter and dark energy, the two dominant components of the cosmos, remain unseen. We can measure their effects. Dark matter holding galaxies together, dark energy driving the expansion, but their nature is unknown. The edge of what we can see does not reveal them directly. They are inferred, hidden within the fabric itself. The horizon limits us not only in space, but in understanding. Still, there is beauty in the very idea. To know that the universe is finite in what we can see but possibly infinite in reality is a reminder of perspective. We occupy one bubble, one viewpoint, one slice of a vast whole. The horizon defines our view, but not the totality. Every night sky, every telescope image, every deep field is framed by this limit, and within that frame lies a universe rich with galaxies, stars, planets, and perhaps life. When you think of travel, whether it's walking across a room or flying across an ocean, there's always a speed involved, a rate at which distance can be crossed. In daily life, speeds are flexible. You can walk slowly or sprint, drive at 50 kilometers per hour or 200, fly in a jet at nearly 1,000. Technology keeps pushing those limits higher. But when you turn to the universe itself, you encounter a speed that is not just a practical limit, but a fundamental one. This is the speed of light. It is the fastest anything can move, the upper bound of motion written into the structure of reality itself. Light travels at about 300,000 kilometers per second. That is so fast that in 1 second, it could circle Earth more than 7 times. It seems instantaneous in daily life. When you turn on a lamp, the room fills with light without delay. But when you apply that speed to cosmic distances, it suddenly feels finite, even slow. Light from the sun takes about 8 minutes to reach us. That means every time you look at the sun, carefully and indirectly, you're seeing it not as it is now, but as it was 8 minutes ago. The moon is about 1¼ light seconds away. The nearest star beyond the sun is 4 light years away, meaning its light began its journey 4 years ago. Across the galaxy, light takes tens of thousands of years to travel. Across the observable universe, billions. The fastest speed possible becomes a measure of time as much as distance. What makes this limit profound is that nothing, not even information, can go faster. You cannot send a message, a particle, or a spacecraft faster than light in a vacuum. It is not just a matter of engineering, it is built into the structure of space-time. Einstein's theory of relativity revealed that as you approach light speed, time slows for you, distances contract, energy requirements rise. To actually reach the speed of light would require infinite energy, which nature does not allow. For anything with mass, light speed is forever out of reach. Only light itself and other massless particles can move at that speed. This limit explains why the universe has a horizon. The observable universe exists because light has only had so much time to travel since the beginning. If faster speeds were possible, we could see farther. But with light speed as the cap, there is always an edge, always a boundary beyond which we cannot see. The speed of light is not just a number. It is the ruler that defines the visible cosmos. It also creates a kind of delay built into existence. We never see anything exactly as it is. We always see it as it was. When you look at the moon, you see it as it was a second ago. When you look at the sun, 8 minutes ago. When you look at Andromeda, 2.5 million years ago. The night sky is not a snapshot of the present, but a tapestry of the past, layered across distances. The farther away something is, the further back in time you're looking. The speed of light ensures that space and time are woven together. To look outward is to look backward. This can be comforting in a way. When a star explodes in a galaxy millions of light years away, its light may just now be reaching us. The event happened long ago, but for us it is happening now. We're constantly receiving stories from the past, delivered at the only speed they can travel. The universe is a vast archive, broadcasting its history across time, each message delayed by the distance it has to cross. It also shapes what is possible for us as travellers. Even if we could build ships that approach the speed of light, The distances are so immense that reaching another star would still take years, decades, or centuries. Voyager 1, the most distant human-made object, moves at over 60,000 kilometers per hour, but at that pace it would take more than 70,000 years to reach Proxima Centauri. Compared to light, our machines crawl. The speed limit reminds us of our scale. Tiny beings on a small planet moving slowly compared to the cosmos. And yet, relativity also adds a twist. For travellers moving close to light speed, time slows down relative to those they leave behind. A ship travelling at near light speed could, in principle, cross to another star in what feels like a manageable time for those on board, while thousands of years pass on Earth. The speed of light is not only a limit, but a boundary where time itself bends. This is why it is so central to modern physics, not just a number, but a principle. Nothing outruns light, and in approaching it, time and space themselves change. Light speed is also why the universe looks the way it does. The light from distant galaxies is stretched as space expands, its wavelength elongated into redder colours. This redshift is how astronomers measure distance and motion. The farther a galaxy, the faster it appears to be receding, not because it is moving through space, but because space itself is stretching. The speed of light, constant and finite, makes this stretching measurable. Without it, we could not map the expansion. Even daily experience depends on this limit. When you look in a mirror, the light reflecting back took a tiny fraction of a second to reach you. When you gaze at a star, its light has been travelling for years. When you use a GPS device, signals travel at light speed between satellites and Earth, and those tiny delays must be accounted for. The speed of light is not only a cosmic principle, but a practical reality woven into technology and navigation. There is a certain poetry in knowing that light itself is both the messenger and the measure. It carries information across the cosmos, and it sets the boundary for how far that information can travel. It defines the size of the observable universe, the shape of time, the possibility of travel. Without it, there would be no horizon, no sense of past and present layered across the stars. And while the speed of light feels impossibly fast to us, in the scale of the universe it becomes a bottleneck. Light crossing a room feels instant. Light crossing the Earth takes a fraction of a second. Light crossing a galaxy takes 100,000 years. Light crossing the observable universe takes almost 14 billion. Even at the maximum possible speed, the cosmos is too large for direct contact across its entirety. That gap ensures that mystery remains, that distance is not just space but time, that the edge of sight is also the edge of knowledge. The speed limit of light is not a barrier meant to frustrate, but a feature of reality that gives the universe its shape. It means the night sky is layered in history. It means we live inside a bubble of vision defined by time. It means travel and communication are forever local, tied to the pace of photons. And it means that even as we look farther, we know there is always more beyond, unseen, waiting in silence. When we speak of the cosmos, we often imagine it as something vast but steady, a great structure stretched out and waiting to be explored. Yet the universe is not fixed. It is not a silent backdrop upon which galaxies sit unmoving. It is dynamic, changing, growing. Space itself is stretching, and has been stretching since the very beginning. This discovery, that the universe is expanding, is one of the most profound shifts in our understanding of existence, because it means the cosmos has a history, an origin, and a future. For much of human history, the universe was assumed to be eternal and unchanging. The stars circled overhead in their regular patterns, the planets wandered but returned, and the Milky Way arched across the sky without alteration. It felt natural to imagine that the universe itself was permanent, that it had always been as it is now. But in the early 20th century, observations began to suggest otherwise. Astronomers looking at distant galaxies noticed something peculiar. Their light was stretched, shifted toward the red end of the spectrum. This red shift was not random. The farther away a galaxy was, the greater the redshift appeared. It was as if all the galaxies were moving away from us, and the more distant they were, the faster they seemed to retreat. Edwin Hubble, in 1929, put the pieces together. He showed that the universe itself is expanding, that galaxies are not racing through static space but being carried apart as space stretches between them. This was a startling idea. It meant the universe had not always been this large. It meant there must have been a time when everything was closer, denser, hotter. That realization gave birth to the theory of the Big Bang, the idea that the universe began from a much smaller, hotter state nearly 14 billion years ago and has been expanding ever since. The image of expansion is sometimes misunderstood. People imagine galaxies flying outward through space like shrapnel from an explosion. But the reality is subtler. It is not that galaxies are rushing outward into empty space. It is that space itself is expanding, carrying galaxies with it. Imagine dots on the surface of a balloon. As the balloon inflates, the dots move farther apart, not because they are moving across the surface, but because the surface itself is stretching. In the same way, galaxies drift apart because the fabric of space is stretching between them. This expansion has been measured with increasing precision. Astronomers calculate the Hubble constant, the rate at which the universe is expanding. Today it is roughly 70 kilometers per second per megaparsec, which means that for every 3 million light-years of distance, galaxies recede an additional 70 kilometers per second. On the largest scales, this adds up to staggering speeds. Galaxies billions of light-years away recede from us faster than the speed of light, not because they are breaking cosmic rules, but because space itself expands between us and them. Their light still reaches us if it began the journey early enough, but beyond a certain point their light can never catch up. They are lost to us, outside the observable horizon. At first, it was assumed that the expansion might slow down over time. Gravity, after all, pulls everything together. The mass of galaxies, gas and dark matter should act as a brake, slowing the expansion as time passed. Perhaps it might even halt someday, and the universe could collapse back in a big crunch. But in the late 1990s, astronomers discovered something unexpected. Observations of distant supernovae revealed that the expansion was not slowing down, it was speeding up. Some unknown force, called dark energy, was pushing galaxies apart faster and faster. The universe was not only expanding but accelerating, and it has been doing so for billions of years. Dark energy remains one of the deepest mysteries in science. It makes up about 70% of the universe's energy content, yet we know almost nothing about it. We only see its effect, the accelerating expansion. Some theories suggest it is a property of space itself, an energy that arises from the vacuum. Others propose that it might change over time. Whatever its nature, its effect is profound. It determines the future of the universe. Because of dark energy, the expansion will not slow and reverse. Instead, it will continue indefinitely. Galaxies not bound to us by gravity will drift farther and farther away, their light redshifted until it fades from view. In trillions of years, distant galaxies will disappear beyond the horizon, leaving only our local group visible. Future astronomers, in that distant era, might not even know the universe is expanding, because everything beyond their group will have vanished from sight. The cosmos will look emptier, not because it is smaller, but because acceleration has stretched the distances beyond reach. This reality changes how we think of the universe. It is not static, but dynamic. It had a beginning, and it will have an unfolding future shaped by expansion. To live in an expanding universe is to exist in a cosmos that is not fixed, but moving, carrying us all outward in a vast drift. What does this mean for us now? It means that when we look at distant galaxies, we are looking at echoes of a time when they were closer. Their light is stretched not only by distance, but by expansion itself. A photon leaving a distant galaxy billions of years ago has been stretched along with space, its wavelength elongated, its energy diluted. This stretching encodes the history of expansion, written into the very colour of the light. By measuring it, astronomers reconstruct the past, tracing how fast the universe grew at different times, learning about its age, its contents, its fate. The discovery that the universe is still expanding and accelerating is one of the greatest surprises in science. It reminds us that the cosmos is not only vast but active, not only immense but changing. The night sky, serene and steady to the human eye, is in truth part of a grand motion, galaxies drifting apart, space itself swelling, time carrying everything outward. And yet, even in this motion, our own corner feels stable. The Milky Way, Andromeda, and other members of the local group are bound by gravity. In a few billion years, Andromeda will merge with the Milky Way, forming a new galaxy. On that scale, expansion does not matter. Gravity wins locally. The expansion only rules on the larger scales, where galaxies are far enough apart that their mutual pull cannot overcome the stretching of space. This dual reality, gravity binding nearby systems, expansion carrying distant ones apart, is part of the beauty of the cosmos. The fact that the universe is still expanding also raises the question of what lies beyond our horizon. If the cosmos is larger than the observable universe, as most evidence suggests, then expansion has carried regions beyond our sight forever. Entire galaxies, perhaps entire structures, lie outside the bubble of what we can see. The universe may be infinite. It may be finite but unbounded, curving in ways we cannot yet detect. The expansion hides those answers from us, sealing them beyond reach. Still, the knowledge we do have is remarkable. A century ago, we thought the universe was static, eternal, perhaps only as large as the Milky Way. Today we know it is expanding, accelerating, and unimaginably vast. This is not only a scientific revolution, but a shift in perspective. To live in a universe that grows is to live in a cosmos with a story, a beginning, and a trajectory. We are part of that unfolding, carried along with every other galaxy, sailing outward on a tide of expanding space. If the universe is still expanding and accelerating, will it expand forever? Does it go on without end, infinite in size and time? Or is there some other shape, some other limit? When you look up at the night sky, the natural question arises, does it ever end? If you could travel far enough, would you eventually come to a wall, an edge, a place where space stops? Or does it continue forever, stretching without limit in every direction? This is the question of infinity, one of the deepest mysteries in cosmology. Infinity is a strange idea, because our daily lives never offer examples of it. Everything we encounter has limits. A road ends. A book has a last page. A lifetime has a beginning and an end. Even the Earth, which once felt endless to those who walked across its continents, eventually reveals itself as round and finite. To imagine something with no boundary, no edge, is to step beyond ordinary thought. Yet when it comes to the universe, infinity may be the reality we live in. The observable universe, as we've seen, is finite in size. It is a bubble 93 billion light-years across, defined by how far light has travelled since the beginning. But that does not mean the universe itself is finite. It only means we can see that much of it. Beyond the horizon, space may continue, perhaps endlessly. The galaxies we see are only a sample, a patch of the whole. The true size may be larger by orders of magnitude, or truly infinite, with no end at all. Astronomers approach this question carefully, because infinity is difficult to test. You cannot measure infinity directly. Instead, you look for clues. One clue lies in the geometry of the universe. Space can curve, just as the surface of Earth curves. If the universe has positive curvature, like the surface of a sphere, it would eventually close on itself, finite but unbounded. If it has negative curvature, like a saddle, it would extend forever, but with a distinct shape. If it is flat, it could be infinite. Measurements of the cosmic microwave background, the afterglow of the Big Bang, suggest that the universe is very close to flat, with no detectable curvature on the larger scales. That finding hints that it may indeed be infinite. But even flat does not guarantee infinity. The universe could be flat yet still wrap around itself in a shape like a torus, repeating like a video game map, endless in travel but finite in content. Or it could extend only so far before curving in ways we have not yet detected. The evidence points strongly toward a cosmos much larger than the observable part, but whether it is truly infinite remains open. Infinity also raises paradoxes. If the universe is infinite and filled with galaxies, then there are infinite stars, infinite planets, infinite possibilities. Somewhere, countless light years away, there could be another Earth, identical in every detail, because in an infinity every arrangement must occur. There could be not only one, but infinite versions of you, living out infinite variations of your life. This sounds like science fiction, but it is a logical consequence of infinity combined with finite arrangements of matter. If matter can only arrange itself in so many ways, then an infinite universe means repetition. This is called the doppelganger, or multiverse interpretation of infinity, and while it stretches imagination, it also shows how strange infinity is. It is not just very large, it is qualitatively different. A realm where probability guarantees duplicates, where rarity is erased by endless repetition. Infinity also reshapes how we think of beginnings and ends. The universe may have started with the Big Bang, but if it is infinite, it was infinite even then. Every region of space was once compressed and hot, but the whole had no edge. Expansion simply stretched what was already unbounded. Similarly, if the universe expands forever, infinity remains. It cannot grow into infinity, because infinity has no larger. It simply continues. There is also the question of whether infinity is real or just a mathematical concept. In mathematics, infinity is well defined, an endless extension. But in physics, we must ask whether the universe itself truly embodies it. Some argue that infinity is not physical, that the universe must be finite in ways we have not yet understood. Others accept it as real, pointing to the flatness of space and the lack of evidence for boundaries. The debate continues and may never be resolved because by definition we cannot observe beyond the horizon. Even without certainty, the thought of infinity has an impact. It makes the universe feel both more overwhelming and more intimate. Overwhelming, because infinity means there is no end, no outer limit, no place where the journey stops. Intimate, because if everything repeats, then every possibility is realized somewhere. The universe becomes a vast mirror, reflecting endless variations of the same patterns. Infinity also changes how we view ourselves. In a finite universe, the Earth might be rare, unique, a single oasis in a desert of stars. In an infinite one, Earths might be countless, scattered like pearls across a limitless sea. Life might not only exist elsewhere but everywhere, repeated in forms both familiar and strange. Infinity turns the question of rarity into one of inevitability, and yet even if infinity is real, our experience is still finite. We live within the observable bubble, the slice of cosmos light has allowed us to see. Our lifetimes are measured in decades, our histories in millennia, our species in a few 100,000 years. Against infinity, these scales are vanishing. The paradox is that we live finite lives in what may be an infinite universe. That contrast is part of the wonder, to be small and bounded, yet able to imagine and describe what has no bound. Some find comfort in infinity, others unease. Comfort because it means there is always more, always farther, always beyond. Unease because infinity is too vast to grasp, too large to give meaning in human terms. But perhaps that is the point. The universe is not obliged to fit our sense of proportion. Infinity, if it exists, is part of its reality. When you hear the word universe, it feels like the final word, the container of everything, the totality of space, time, matter, and energy. For centuries, that was how people thought of it. One cosmos, all that exists, the sum of everything. But in recent decades, a new idea has emerged, an idea both fascinating and unsettling. What if our universe is not the only one? What if it is just one among many, part of a wider collection we call the multiverse? The notion of other universes sounds like speculation, and in many ways it is, because we have no direct evidence of them. But science entertains the idea for serious reasons. One reason comes from inflation, the theory of the universe's earliest moments. Inflation suggests that in the first fraction of a second after the Big Bang, space expanded at an enormous rate, far faster than at any time since. This rapid inflation smoothed out the cosmos, explaining why the universe looks so uniform on large scales today. But inflation also predicts that different regions of space could have inflated differently, creating multiple bubble universes, each with its own properties. Our observable universe would be just one bubble in an endless froth, each bubble a universe in its own right. Another reason comes from the fine-tuning of physical laws. Our universe has constants, the strength of gravity, the charge of the electron, the speed of light, that allow stars, planets, and life to exist. If these constants were slightly different, the universe might be sterile, with no complex structures. Why do they have the values they do? Some physicists suggest that if there are many universes, each with different constants, then it is not surprising that we find ourselves in one where conditions allow life. In a multiverse, fine-tuning is explained by selection. We are here because this universe permits it. The idea also arises in quantum mechanics, where the mathematics suggest that every possible outcome of an event might occur in some branch of reality. This interpretation, sometimes called the many worlds view, implies that the universe constantly splits, creating parallel versions for every possibility. In one, you made a different choice. In another, a star exploded earlier or later. In another, Earth followed a different history. These parallel universes, if real, would be inaccessible to us, yet part of the total structure of reality. Of course, these are theories, not proven facts. The challenge with other universes is that, by definition, they may be beyond observation. If they exist outside our cosmic horizon, we cannot see them, no matter how powerful our telescopes. They are forever cut off, their light unable to reach us. That makes them difficult to test, and some scientists argue that without evidence, the multiverse is speculation. Others counter that if the mathematics of our best theories implies them, we should take the idea seriously, even if direct observation is impossible. Still, the thought itself is profound. Imagine that beyond our observable universe, there are countless others, each with its own galaxies, stars, and perhaps life. Some might be similar to ours, others might be radically different, with different laws of physics, different forms of matter, even different dimensions. Infinity could mean not just endless versions of this universe, but endless varieties of universes altogether. It also changes how we think of uniqueness. If there are other universes, then perhaps our cosmos is not special. It is one of many, a single bubble in a vast sea. Yet within it, we are unique, because this is the universe we inhabit, the one whose stars warm us, whose galaxies we see in the night sky. Other universes may exist, but they are not ours. This one is the place where our stories unfold. Some cosmologists search for indirect hints. If another universe once collided with ours, it might have left a scar, a pattern in the cosmic microwave background. Some have looked for such imprints, though none are confirmed. Others search for signs in particle physics, where extra dimensions or unusual symmetries could hint at a larger multiverse. None of this is certain. For now, the existence of other universes remains a question, not an answer. But even as a question, it has power. It stretches imagination. It pushes science to its limits. It makes us confront what everything really means. If the universe is not all there is, then our perspective changes again. We're not only small compared to the cosmos, but our cosmos itself is small compared to a greater whole. The multiverse, if real, would be the ultimate expansion of scale, a step beyond even infinity as we usually think of it. And perhaps this is where curiosity matters most. Whether or not other universes exist, asking the question reminds us that our own is not yet fully understood. There are mysteries still unfolding. Dark matter, dark energy, the shape of space, the fate of expansion. To wonder about other universes is not to abandon this one, but to see it in a wider context. It is to realize that what we know may be only the beginning of what is possible. When you step outside and look up, you do not see other universes. You see stars, galaxies, the faint smear of the Milky Way. You see what belongs to our cosmos. But in your thoughts, you can imagine more. Bubbles beyond bubbles, layers beyond layers, a multiverse stretching beyond comprehension. Whether it exists or not, the thought itself is part of our exploration, a way of reaching past the limits of sight. The journey naturally leads to another question, one perhaps even more mysterious. How did all of this begin? Where did the universe or multiverse come from? What was the origin of everything? When you stand under the night sky, what you see is both impossibly large and deeply personal. The universe stretches in every direction, filled with galaxies beyond counting, woven into filaments, expanding outward without end. Yet from where you are, on a small planet orbiting an ordinary star, it also feels like something intimate, something that belongs to you as much as you belong to it. This contrast between the immensity of the cosmos and the smallness of human life is at the heart of the human perspective. We are tiny compared to the scale of the universe. The Earth itself is a speck against the Milky Way. The Milky Way is a speck against the cosmic web. Our lifetimes are blinks compared to the ages of stars. Civilizations rise and fall in less time than it takes the sun to circle the galaxy once. On paper, in numbers, in comparisons, our scale almost disappears. It is tempting to think that this smallness means insignificance, that against billions of galaxies and trillions of stars a single human life could not matter. And yet, when you pause, you realize that perspective changes everything. Yes, we are small, but we are also aware. We are creatures who can look outward, measure, imagine, and describe. The atoms that make up our bodies were forged in stars. The calcium in your bones, the iron in your blood, the oxygen you breathe. All of them were created in nuclear furnaces long before Earth existed. You are literally made of stardust, assembled by the universe, and now able to look back and ask what it is. That is not insignificance. That is participation. The human perspective is not only about our scale compared to the cosmos, but about how we experience it. A star billions of light years away is a faint point of light to a telescope, but to you it can be a moment of wonder, a story to carry, a spark of curiosity. A photograph of a distant galaxy cluster is not just data. It is a glimpse into time, a reminder that the universe existed long before us and will continue long after. That reminder does not diminish life, it enriches it. It gives a context in which our days, though short, feel like part of something enduring. Consider the way we name and describe the sky. Ancient people traced constellations, patterns of animals and heroes across the stars. They told stories to explain their positions, their motions, their changes. They used the heavens as a calendar, a compass, a guide for planting, sailing, living. The stars were never just distant suns. They were woven into human culture, memory and meaning. Even today, with telescopes revealing their true nature, we still look up with that same blend of science and story. We see both data and beauty, fact and meaning. The human perspective is not only measurement, it is also imagination. This ability to imagine may be our most important link to the cosmos. We cannot cross the galaxy, but we can picture it. We cannot see beyond the observable universe, but we can conceive of infinity. We cannot touch other universes if they exist, but we can wonder about them. Our minds expand where our bodies cannot. That expansion is part of being human, part of what makes our small lives vast in their own way. At the same time, the human perspective is grounded in the everyday. The stars you see tonight are not abstract. They are part of the sky you know, the seasons you live in, the moments you share. The same sky that holds galaxies billions of light years away also holds the moon you walk under, the sun that warms you, the constellations you recognize from childhood. The vastness and the intimacy coexist. The universe is both out there and here, both unreachable and immediate. This duality shapes how we feel about the cosmos. Some nights, you might look up and feel small, humbled by the immensity. Other nights, you might feel connected, part of a whole so vast it includes you. Both responses are valid. Both are part of what it means to be human in a universe like this. The human perspective also includes a sense of responsibility. We are the only species, as far as we know, capable of understanding the universe in this way. That makes Earth not just our home, but the home of the universe's awareness of itself. When Carl Sagan called Earth a pale blue dot, he meant not only that it is small, but that it is precious. It is the stage on which life and thought exist, at least in this corner of the cosmos. Protecting it, cherishing it, is part of cherishing the universe itself, and yet the perspective is also fragile. For most of history, humans lived without knowing the scale of the cosmos. We thought the Earth was the centre, the stars close overhead, the universe a small dome. Only recently have we expanded that view to galaxies, clusters, superclusters, the cosmic web. In the span of a century, our horizon has grown from a single galaxy to trillions. That shift is not just scientific, it is emotional, cultural, philosophical. It changes how we think about ourselves. It challenges us to place meaning not in size or duration, but in awareness and experience. Perhaps the most human part of the perspective is that we never stop asking questions. What is beyond the edge? Why is there something rather than nothing? How did the laws of physics come to be? These are not questions with easy answers, but the act of asking them is part of what it means to be us. Other animals live in the same universe, but as far as we know, they do not wonder about it. Wonder is uniquely human, a way of connecting our finite lives to infinite possibilities. And in that sense, the human perspective is not small at all. It is vast, because through thought, imagination, science, and story, we reach across billions of light years, we touch the beginning of time, we speculate about infinity, we carry the universe inside our minds. The scale may dwarf us, but our ability to think about it gives us a kind of scale of our own. When you stand under the stars, remember this: you are not apart from the universe, you are part of it. You are a collection of atoms born in ancient stars shaped by cosmic history, alive for a brief span, able to see and feel and wonder. The human perspective is not about being the centre, it is about being a participant, a witness, a voice within the vastness. And though the cosmos will continue long after us, though galaxies will drift beyond view, though stars will burn out and black holes will fade, the fact remains that here and now, in this corner, awareness exists. That awareness is you. That awareness is us. In the great sweep of time and space, it is a fleeting spark. But a spark, even small, still lights the dark. You've been drifting now through stars and galaxies, through filaments of light and oceans of emptiness, through horizons defined by time itself. The universe is larger than our senses can hold, larger than our words can capture, and yet, here you are, listening, breathing, present within it, part of the very fabric you've been imagining. The scale has stretched outward from planets to galaxies to webs across billions of light years, and somehow it all still leads back to you. A conscious being resting on a small planet, turning slowly beneath the night sky. It's easy to lose yourself in the vastness, to let the numbers roll past, the billions and trillions, the distances that stretch beyond imagining. They are real, but they're also metaphors pointing at a truth too wide for language. What matters in this moment is not just that the universe is immense, but that you have felt its immensity. You've carried your mind outward, step by step from the familiar neighbourhood of planets to the horizon of the observable cosmos. That act of thought is itself remarkable. No matter how small the body, the mind can hold galaxies. The night sky above you, wherever you are, is not abstract. It is the real connection between you and everything you've heard. The stars you see are suns within our galaxy. The faint streak of the Milky Way is the shape of our home. Somewhere beyond sight, Andromeda drifts toward us, a future encounter written into the dance of galaxies. Farther still, clusters and filaments stretch across the dark. All of it exists now, all of it real, even if hidden beyond vision. And you, lying beneath the sky, are part of it all. You might notice, as you think of this, that your breathing has slowed, that your body feels heavier, anchored, safe. The immensity above is not something to fear. It has carried you this far already. Every atom of your body has travelled through billions of years to arrive here. The calcium in your bones once lay in the heart of a star. The oxygen in your lungs was forged in an ancient furnace. You're not only in the universe is in you. That connection makes the distance feel less cold. It turns the silence of space into something familiar, something shared. Imagine again the horizon of the observable universe, that 93 billion light-year bubble surrounding us. It might sound vast beyond hope of understanding, but within it lies every galaxy, every star, every planet, every breath of air, every sound you've ever heard. The edge is not an end. It is simply the limit of sight. Beyond it, space continues, carrying more than we can ever know. But here, within this bubble, life exists. Consciousness exists. You exist. And that is extraordinary enough. You might find yourself wondering what it means, all of this immensity compared to one quiet human life. The answer is not in numbers, but in moments. The warmth of sunlight on your skin, the sound of a familiar voice, the rhythm of your heartbeat, the calm of resting now. These are not less important because the universe is large. They are more precious because they are fleeting, because they are yours. There is comfort in the idea that the cosmos is so much larger than us. It means we are carried, part of a vast unfolding, not responsible for holding it all together. It continues whether we think of it or not, and yet, by thinking of it, we join it more deeply. The human perspective is not about control, but about connection. Tonight, by listening, you have connected, not by travelling billions of light years, but by allowing your mind to travel outward, calmly, slowly, step by step. As you settle now, you can let go of the numbers, the distances, the horizons. You can let the images of galaxies fade into something softer, like the afterglow of a dream. You have walked far enough into immensity. You can return now to your own breath, your own body, your own moment. The same universe that holds galaxies also holds this pause, this rest, this quiet. There is no separation between them. You're small compared to the cosmos, yes, but you're also vast in your ability to imagine, to wonder, to feel awe. Both truths are real. Both belong to you, and as you close your eyes, you carry them with you, the enormity of everything and the stillness of now. So let yourself rest. The galaxies will continue their drift. The stars will burn and fade. The universe will expand. And here, tonight, you're safe within it, part of it, exactly where you're meant to be.